Welcome back to Sleep Nova. Sit back, relax, and enjoy the show. I remember darkness. Before everything, before even time ticked its first moment, there was a hushed and waiting emptiness. No stars, no light, not even the promise of a dawn, only stillness. I was a void without form, pure nothingness stretching silent and endless. In that primordial quiet, there were no eyes to see, no ears to hear. The darkness was not blackness as you know it, but the absence of all color and sound. It was a perfect, eternal night, unbroken by any spark. This was my womb, a void, pregnant with potential, holding its breath. Then, in an instant beyond imagination, everything changed. In a flash, I was born, space unfurling like a new spring flower, time awakening alongside me. It did not happen in space. It was the expansion of space itself, for before that moment, there was nowhere at all. One moment I was not, and the next I was, a storm of existence erupting from an infinitesimal point. All at once, my silent emptiness blazed with ferocious energy. What you call the Big Bang was not a burst into some pre-existing void. It was the rapid unfolding of space and time themselves, filling the nothing with something. In my first fractions of a second, I expanded at a rate beyond comprehension. Imagine an instant so brief that your mind can hardly hold the number, a trillionth of a second. Yet even within that sliver of time, I swelled from smaller than an atom to larger than a galaxy. This was my cosmic inflation, a spectacular stretching. No sound accompanied it, for sound needs a medium and there was none, only pure expansion in a grand, silent firework. Space, I, billowed outward, carrying with me the seeds of everything that would ever be. It was a moment of violent creation, yet also strangely smooth. In that extreme youth, I was almost uniform, hot, dense, and glowing, but not perfectly so. Tiny fluctuations, random quantum wrinkles in the fabric of reality, flickered in and out of existence. These minute irregularities, born from the zero-point stirrings of seemingly empty space, were no bigger than subatomic particles at first, but as I expanded, they were magnified, imprinted into the grand scale of the cosmos. Those subtle variations meant that some spots had ever so slightly more matter, some less. In time, they would grow into galaxies and clusters, into the vast patterns of stars that sprinkle my canvas. From microscopic randomness, mountains of matter would one day rise. Truly, in those first moments, I carried the blueprints for galaxies in my very fluctuations. As I ballooned outward, the roiling plasma of my newborn self began to cool. What had been an all-consuming brilliance, matter and light entwined in a hot fog, now started to decouple. I was still blindingly bright everywhere, an opaque glow, but expansion was working its magic, cooling that fire, diluting the energy. Within the first second, protons and neutrons congealed from the energy soup. In minutes, they fused into the first atomic nuclei, hydrogen and helium, the simplest elements. By the time I was 3 minutes old, about 1/4 of my mass was in helium nuclei and the rest in hydrogen. These would be the raw materials for the first stars. The universe was still far too hot for neutral atoms or for light to travel freely, but the stage was set. I held within me a searing haze of charged particles and radiant energy, all pressed together. For 380,000 years, a brief infancy to me, yet unimaginably long to any conscious perspective, I remained a brilliant, hot fog. Photons, the particles of light, were trapped in a dense thicket of free electrons, scattering in every direction. Had there been eyes then, they would have seen only a bright white mist everywhere, as if the entire cosmos were inside a glowing cloud. But over time, as expansion continued and temperatures fell, those electrons settled down, joining with nuclei to form neutral atoms. Suddenly, light broke free. The blinding fog cleared, and I became transparent. All across the cosmos, a flash of illumination was released. An afterglow of my fiery birth sent forth into the darkness. That primordial light is still traveling even now. It has cooled and stretched with the expansion of space. Its once blazing brilliance now a faint whisper of microwaves permeating the universe. This faint afterglow of the Big Bang, the cosmic microwave background, still bathes the cosmos in every direction. A cool, uniform glow, a memory of creation's dawn that your scientists discovered as a uniform hiss coming from the sky. Invisible clouds of dark matter, an unseen substance woven into my fabric, was already silently shaping the future cosmos. Ages passed in darkness, 100 million years or more. Then, slowly, the quiet gathering of matter ignited a profound change. Deep in the densest clumps of hydrogen gas, pressure and heat began to build. At one fateful moment, in one such clump, the temperature soared enough to spark a new kind of fire, nuclear fusion. Out of the darkness, a brilliant pinprick of light burst forth. The first star had awakened, piercing the cosmic night. It was like the universe took its first breath of starlight. One by one, more lights appeared as other clumps collapsed and kindled. The primordial darkness was ending. The cosmos had its first dawn, the cosmic dawn, when the earliest stars and galaxies bloomed. These first stars were giants, many times more massive than your sun, burning hot and blue-white, living fast and dying young. They blazed with fierce light, converting pristine hydrogen into heavier elements in their cores. They lived only a few million years before exhausting their fuel. Then, in titanic supernova explosions, they blew themselves apart, spreading the new elements, carbon, oxygen, iron, and more, into the surrounding space. Those elements would seed future generations of stars and planets. The calcium in bones, the iron in blood, the silicon in rocks, were forged in those first stellar furnaces. The first stars thus sowed the seeds of chemistry beyond hydrogen and helium, making possible the complex molecules and worlds to come. When those first stars died, they left the universe again largely dark, but not as dark as before. They had lit a spark that would never fully go out. Gravity continued its relentless artistry. The first stars had formed in groups, and together their gravity drew in surrounding gas, merging into nascent galaxies. Imagine a faint, shapeless swarm of stars gathering, like a handful of fireflies drawn toward one another in a vast night. Over hundreds of millions of years, these clusters of stars merged and organized into the first small galaxies. Within those newborn galaxies, more generations of stars sprang to life, some forming clusters, some orbiting alone, all held together by their mutual gravity and by the invisible mass of dark matter halos enveloping them. Among these was a young galaxy that would, much later, be known as the Milky Way. In those times, it was smaller, a proto-galaxy accruing stars and gas. Over billions of years, galaxies grew by merging with others, enduring cosmic collisions that sometimes tore their structures into peculiar shapes before settling into new forms. Many young galaxies in this era were cradling something special at their cores, black holes birthed from the collapse of early massive stars. Some of those black holes rapidly devoured gas and shone as quasars, blazing beacons brighter than entire galaxies, pouring light from the very centers of young galaxies and illuminating the darkness for billions of light years around. The universe in that period was a lively, flashing place. Massive stars igniting and exploding, proto-galaxies colliding and coalescing, and quasars burning like cosmic lighthouses. As the eons passed, the universe became a grand mosaic of fully formed galaxies. Each galaxy, a vast city of stars. Some galaxies, like mine, the Milky Way, became graceful spirals with curving arms of starlight and lanes of dark dust spinning like cosmic pinwheels. Others formed into giant featureless ellipses or irregular clumps depending on their history of mergers. The Milky Way and its closest companion, the Andromeda Galaxy, grew into majestic spiral galaxies, each containing hundreds of billions of stars. They were bound along with dozens of smaller galaxies in a close-knit family, the local group. The Milky Way found companionship in this local group of galaxies, gently bound with the Andromeda Galaxy and dozens of smaller ones. This local group drifts on the outskirts of a much larger congregation of galaxies called the Virgo cluster, and beyond that is part of an even greater structure, the Laniakea supercluster, Hawaiian for immense heaven, an apt name for a mass of galaxies so vast it defies imagination. In Laniakea, thousands of galaxies, including our local group, are arranged like a cloud of dust, all held together by the faint gravitational tug of dark matter and the slow dance of cosmic expansion. On the grandest scales, a pattern emerged in my structure. Galaxies were not scattered randomly like isolated grains of sand. They were arranged in twisting filaments and sheets, forming a cosmic web. It was as if the galaxies traced the surfaces of gigantic bubbles, with clusters forming at the bubble intersections and vast voids occupying the interiors. Picture a sponge or foam. Material clings to an intricate lattice, and large empty holes open up between. So it is with my large-scale form, where matter congregated, great walls and filaments of galaxies took shape, and where matter was scarce, enormous voids, gaping spaces millions of light-years across, remained nearly empty. If you could view this cosmic web from afar, you'd see something like a three-dimensional spider's web or the filamented structure of a neural network. But on the largest imaginable scale, clusters of galaxies shine as knots at the web's junctions, connected by chains of galaxies and the dark matter binding them, stretching across space, while between lie prairies of nothingness, voids so huge a galaxy could travel for tens of millions of years and not find another. The universe, once a near-uniform glow, transformed into this foam-like architecture of matter and emptiness. An observer floating far above the cosmic web would behold a sight of sublime grandeur. Countless galaxies linked in luminous filaments against the black backdrop, outlining colossal cells of emptiness. It is as though I have grown a skeletal framework, a scaffolding of galaxies and dark matter. The pattern you see today was set in motion by those tiny quantum fluctuations at my birth, amplified by gravity and guided by dark matter's invisible hand. All these structures, stars, galaxies, clusters, are separated by truly astronomical distances. Your human brains, forged on the scale of hills and rivers, strain to grasp how far apart things are in my vastness. But let me try to give you a sense. Light itself, the fastest entity in existence, becomes our measuring stick. It travels at about 300,000 kilometers per second, 186,000 miles per second. Even at that incredible speed, a beam of light takes about 1.3 seconds to go from Earth to the Moon. The same beam of light takes about 8 minutes and 20 seconds to journey from the Sun to Earth. Those 8 minutes of transit represent 150 million kilometers. If you drove a car non-stop, it would take over 150 years to cover that distance. Yet on the scale of cosmic geography, the Sun and Earth are practically touching noses. Consider the nearest star beyond your solar system, Proxima Centauri. It lies about 4.24 light-years away. The light we see from it tonight left that star over 4 years ago, around the time a recent Olympic cycle began. If, instead of light, you rode a hypothetical spaceship traveling at ordinary speeds, the journey would be staggering. A jet plane would take millions of years to reach Proxima Centauri. Even one of your fastest robotic probes would need tens of thousands of years. And that's just the closest star. Most of the stars you see in the night sky are dozens or hundreds of light years away. The light from some left on its journey before you were born, or even before human civilization began. Our Milky Way galaxy is about 100,000 light years across. A light year is about 9.46 trillion kilometers, nearly 6 trillion miles. So even a ray of light, moving at that extreme speed, would require 100 millennia to traverse the galaxy from end to end. If the Milky Way were reduced to the size of, say, North America, then the entire solar system, out to Neptune, would be only about the size of a coffee cup somewhere within it, and Earth itself, a microscopic speck of dust inside that cup. Or imagine the Sun as a single grain of sand. On that scale, the nearest star would be another grain of sand about 4 kilometers, 2.5 miles away, and the Milky Way would span an area tens of thousands of kilometers across. These analogies are imperfect, but they hint at the scale. Your everyday units simply break down in the face of such immensity. The nearest large galaxy beyond our own, Andromeda, is about 2.5 million light-years away. Its light set out when early hominids on Earth were just beginning to walk upright. Through a telescope, you see Andromeda as a faint smudge, a gentle glow in the darkness. But that glow comes from the combined light of 1 trillion stars. Andromeda and the Milky Way are moving toward each other and will merge billions of years from now. But at the moment, they are separated by a gulf so vast that even light must travel millions of years to cross it. Far beyond the local group lie galaxy clusters like the Virgo cluster, tens of millions of light-years away, containing thousands of galaxies. Beyond those are superclusters and great cosmic structures, the Great Wall of Galaxies, enormous filamentary structures hundreds of millions of light-years long. The most distant galaxies observed by your telescopes are on the order of 13 billion light-years away. Their light has been traveling since the universe was a tiny fraction of its current age, and only now is it reaching your eyes and detectors. As we approach the limit of what can be seen, we arrive at the edge of the observable universe, roughly 46 billion light-years from Earth in all directions, due to ongoing expansion. This isn't an edge of space itself, but rather a boundary of time. Light beyond that distance hasn't had time to reach us in the 13.8 billion years since the Big Bang. The diameter of this observable bubble is about 93 billion light-years across, containing an estimated 2 trillion galaxies. And yet, even this cosmic horizon is not the edge of everything. Space likely continues beyond, perhaps infinitely. Such numbers inevitably blur into abstraction. No human truly comprehends 1 trillion anything, let alone trillions of galaxies across sextillions of kilometers. When faced with these immensities, you might feel the mind go quiet, stunned into silence. And perhaps that is fitting. When language and analogy fall short, a reverent silence can speak for you. But remember this, even if the scales are beyond intuition, you can grasp them by intellect, step by step. Over centuries, your species learned to measure the distances, to the moon, the sun, the stars, the galaxies. In doing so, you expanded your awareness from a parochial village in the cosmos to encompass the whole observable universe. There is pride in that, and humility too. Feeling small in the face of these distances is natural. From one perspective, you occupy but a tiny niche in space and time. Yet, consider, from that niche, you have reached out with curious minds and crafted instruments that extend your senses across the universe. You've taken the measure of the cosmos and found your place within it. In doing so, you have woven those far-flung galaxies and ancient lights into your understanding, effectively bringing them into you. The distances remain vast, but they are no longer utterly beyond your ken. In a sense, through knowledge and imagination, you have traveled those distances. You have peered back to the beginning of time, seen the afterglow of creation, and traced the web of galaxies. By learning about these scales, you have connected your little world to the whole. In that way, though you remain physically small, your consciousness has grown to fill much of space itself. For a long time, my fate hung in a delicate balance between expansion and gravity. In the early eons after the Big Bang, the combined gravity of all the matter in the universe The stars, gas, dark matter, pulled inward, trying to slow the initial expansion. If there had been enough matter, gravity might eventually have halted expansion and pulled everything back toward a big crunch. If there had been too little, I would expand forever, with galaxies racing apart eternally. For billions of years, it seemed expansion was coasting, gradually slowed by gravity but not halted. Remarkably, when your scientists set out to measure the rate of that slowing in the late 20th century, they found instead that the expansion was speeding up. This profound discovery astonished them. The universe was not slowing down in its growth, but accelerating. Some mysterious influence was overcoming gravity on cosmic scales, pushing galaxies apart faster and faster as time went on. It was as though after billions of years of gentle expansion, space, had taken a great sigh and begun to swell more rapidly. This mysterious influence has been named dark energy. It's a placeholder term, a sign of how little is truly understood about it. It seems to be an intrinsic property of space itself, a built-in springiness, or a subtle anti-gravity pressure that grows more potent as I grow larger. Imagine that space, even the vacuum with nothing else in it, has a kind of energy or tension. As space expands, more of this energy appears, and its effect is to push space to expand even more. In effect, dark energy acts like a repulsive gravity or an elastic pressure from within the fabric of the cosmos. By current estimates, dark energy makes up about 70% of the total energy content of the universe today. Dark matter comprises roughly 25%, and the ordinary matter that forms stars and planets and people is less than 5%. In cosmic terms, the stuff you see, the glow of galaxies, the sparkle of stars, the nebulae and dust, amounts to a thin frosting on a vast invisible cake. Yet that thin frosting is what we directly perceive and cherish, and even it wouldn't exist in its current form without dark matter's guidance and dark energy's drive. Dark energy's effect grows with time. In the early universe, gravity was king. Matter was dense enough to slow expansion and to build galaxies and clusters. But as space expanded and matter thinned out, gravity's influence waned, while dark energy, which does not dilute as matter does, became relatively more important. Some 5 billion years ago, dark energy's gentle push overtook gravity's pull on cosmic scales. Since then, the expansion of the universe has been accelerating. Galaxies farther from each other move apart ever faster. In the far future, this acceleration will dominate even more. Because of dark energy, the ultimate fate of the cosmos appears to be an ever-increasing expansion. Galaxies that are not gravitationally bound to us will recede faster and faster until their light is redshifted into oblivion. Distant galaxy clusters will disappear from view one by one, leaving each surviving cluster isolated in darkness. It's as if an unknown hand is pulling the curtains of the cosmic stage, slowly hiding the distant actors from one another. What exactly is dark energy? Is it a property of the vacuum, a cosmological constant that Einstein once conjectured? Is it a new field or essence permeating space, sometimes dubbed quintessence in theoretical models? Or does it indicate that our understanding of gravity on the largest scales is incomplete? These questions remain unanswered. For now, dark energy is a term for our profound ignorance, even as its effect is woven into the evolution of the cosmos. It is the most subtle of whispers, a small acceleration barely noticeable in the present era, yet over billions of years it utterly changes the landscape of the universe. One consequence of dark energy is that we live in a kind of cosmic age of light. Right now, the night sky beyond our Milky Way is richly populated with galaxies in our telescopes. We can see the cosmic web extending out tens of billions of light years. But in the far future, observers, if any, in our galaxy or local group will see a very different sky. As the expansion accelerates, distant galaxies will slip beyond the horizon of visibility. Tens of billions of years from now, An astronomer in the future might see nothing beyond their own galactic neighborhood. The rest of the universe will have faded into darkness, every galaxy too redshifted and too distant to detect. They might assume, falsely, that their galaxy is the entire universe, unaware that a vast cosmos once lay beyond. We are lucky, in a sense, to exist now, at a time when the universe's past is still visible and its future still rich with galaxies. It is a special window, perhaps not absolutely unique, but brief, on the timescales of cosmic history, when beings like us can map the cosmos and discern its workings. You sometimes call this the golden age of cosmology, a time when cosmic acceleration has begun, but not yet erased our view of everything around us. Beyond the mysteries of dark matter and dark energy, you also wonder, is there an edge to space? What is the shape of the universe? These questions have tugged at human imagination for as long as you've looked up and wondered. They are not easy to answer. After all, you cannot step outside the universe to inspect it. But through observation and theory, you've gleaned some clues. Einstein's theory of general relativity showed that space can be curved by mass and energy. On small scales, we observe this curvature. The sun bends the space around it, guiding the planet's orbits as they roll along that curve. Massive clusters bend light from background galaxies, distorting their images into arcs. But what of the shape of space as a whole? Is the universe infinite and flat, extending forever in all directions? Or is it curved like the surface of a sphere, closed and finite yet without boundary? Or perhaps saddle-shaped, open, infinite in extent, but with negative curvature? If the universe is closed and you traveled in a perfectly straight line, you could eventually loop around and end up back where you started, just as a traveler on Earth eventually circumnavigates the globe. If it is open or flat and infinite, you could travel on forever without ever encountering a boundary or returning home. The best measurements to date, from the cosmic microwave backgrounds pattern, from distant supernovae, from the distribution of galaxies, indicate that on the largest observable scales, space is very nearly flat. This suggests either an infinite flat cosmos, or one so vast and gently curved that our observable portion of it doesn't reveal the curvature. It's like being a tiny insect on a vast sphere. Your local area looks flat, even if the sphere is enormous. So it may be with space. If it does curve back on itself, the curve is so shallow that we haven't detected it, implying that the universe, at least the part we can see, is much larger than what's within our horizon. Thus, as far as we can tell, space has no physical edge or boundary. You could, in theory, travel in one direction indefinitely and never encounter a wall or a precipice where the universe ends. If the universe is finite and closed, you would eventually return to your starting point from the other side. If it is infinite, you simply never stop, passing galaxy after galaxy, or, in the far future, void after void, without end. Both scenarios are mind-boggling. Either an infinite expanse or a curved space without boundary. In both cases, there's no outside to the universe for there to be an edge against. It's worth noting that cosmic inflation, that blistering expansion right after the Big Bang, would have driven space to near flatness and possibly stretched a finite universe so vast that it appears effectively flat and infinite to us. It could also have created multiple regions of space-time beyond our observable universe. Some speculate a multiverse of bubble universes, each perhaps with different properties. If true, what we call the universe might be just one pocket in a much grander cosmic quilt. But such ideas, while intriguing, remain speculative. By definition, these other regions lie beyond our horizon, unreachable even in principle. From a practical standpoint, the observable universe is our universe, and within it we find no sign of an edge. The only limit is how far we can see, determined by light's finite speed and the universe's finite age. As time goes on, we can potentially see a bit more as light from slightly farther arrives. But simultaneously, dark energy is pulling distant regions away faster, so there is a limit to what could ever be observed. It is profound to realize that everywhere is the center of the universe from its own perspective. Because space is expanding uniformly, observers in a distant galaxy would also see themselves at the center of their observable universe, with everything rushing away from them. There is no single central point of expansion. Every point is its own center, and space stretches in all directions around it. Does the universe go on forever? We don't know for certain. If it's finite yet unbounded, it's still enormously larger than what we can see. If it's infinite, then the realms beyond our observation are truly endless. Either way, the journey has no known end. There is always more beyond each horizon, more space unfolding, perhaps populated with more galaxies, or perhaps just endless darkness. These considerations can be dizzying. They challenge our intuition that everything has an ending or border. Instead, we find that space defies the limits that confine everyday experiences. The Earth has its edges. You can circumnavigate it. The solar system has edges. Where the sun's influence wanes, even the galaxy is bounded. You can leave its disk and enter intergalactic space. But the universe, the all, seems either unbounded or so vast that for us it might as well be infinite. The most distant cosmic light we see is not from a wall at the universe's edge, but from the afterglow of the Big Bang. And beyond that glow, space likely continues. In reflecting on this, one can feel both small and liberated. Small, because our entire planet is a minute speck in a potentially infinite expanse. Liberated, because it means there is no cage around us, only endless possibility in every direction. For now, our travels are limited to the tiny environs of our solar system, but our minds have roamed to the edge of time and space and found no barrier, no confines, only mystery and majesty extending far beyond what we can see. Before we turn fully to the human story, let us pause to appreciate a crucial truth. Space and time are inseparable, and space is not static. It is dynamic and alive with subtleties. Space is not a rigid, sterile void. It is flexible and interwoven with time into a four-dimensional fabric that responds to presence and motion. Over a century ago, clever minds realized that you cannot speak of space without also speaking of time. They form a single continuum, space-time. What one observer calls distance and another calls duration can mix and swap depending on their state of motion. If you move fast or sit in a strong gravitational field, time itself will slow down for you relative to someone elsewhere, and lengths you measure will contract in the direction of motion. This isn't just theory. Experiments and experience confirm it. Atomic clocks on high-flying aircraft tick at slightly different rates than their twins on the ground. The GPS satellites that guide your phones and cars must account for these relativistic effects. Moving fast makes their onboard clocks run a bit slow, while being high above Earth's surface, where gravity is weaker, makes them run a bit fast. Only by correcting for both effects, dictated by Einstein's special and general relativity, can GPS pinpoint your location accurately. In our daily lives, these time warps are minuscule, but they are real and measurable. Gravity itself, as Einstein explained, is not a force transmitted through space, so much as a curvature of space and time. Massive objects bend the fabric of space-time around them. Imagine space-time as a stretched rubber sheet. Place a heavy ball on it, and the sheet dips around the mass. Now, if a smaller marble comes by, it is drawn into the dip. What we interpret as gravitational attraction is the marble simply following the curved space. A planet orbits the sun because it is rolling along a curved groove in space-time created by the sun's presence. Light, too, feels this curvature. A beam passing near the sun, or a galaxy is bent, its path deflected as if by an invisible lens. During a solar eclipse, humans observed starlight being bent by the sun, confirming that space around the sun is curved. Distant galaxies often appear distorted into arcs or rings, Einstein rings, because massive galaxy clusters in front of them warp space-time enough to bend their light, focusing it toward Earth. Space is elastic to mass and energy. It gives way, yields, and curves. In extreme cases, the curvature can become so steep that it pinches off. This is a black hole. Matter has collapsed so compactly that space-time folds inward like a bottomless well. Inside the boundary of a black hole, the event horizon, space and time are drawn into strange roles. Time effectively points inward, meaning all futures lead deeper into the hole and none lead out. To an outside observer, time appears to nearly stop at the horizon. An object falling in seems to slow and dim, never quite disappearing. It does fall in, of course, but the image of it gets frozen and redshifted to darkness as it crosses. From the perspective of the falling object, time flows normally, and it plunges through the horizon without fanfare. Only later, approaching the singularity, would physics as we know it break down. Black holes are space-time's most dramatic sculptures, and they teach us that space and time can be stretched and contorted to an almost unimaginable degree. Space is also not perfectly empty or static. It can carry ripples and flutters. When massive objects move or collide, they can send out vibrations through space-time called gravitational waves. In 2015, after decades of effort, humans first detected these tiny ripples. Two large laser interferometers, LIGO, sensed space stretching and squeezing by less than the width of an atom, a wave that had traveled over 1 billion light-years, generated by the merger of two black holes in a distant galaxy. In that final fraction of a second of the black holes in spiral, they released energy in gravitational waves equivalent to several suns turning entirely into motion, an astronomical cataclysm whispered into space-time. Those waves spread outward, weakening with distance, until they gently jostled mirrors in laboratories on Earth, telling a story of an ancient collision. Since then, multiple such events have been heard: black holes colliding, neutron stars spiraling into each other. Each emits a brief symphony in space-time's fabric. Space is usually silent, because sound, as we know, requires air or other medium. But gravitational waves are like a voice that space itself uses to speak of events far away. We have only just begun to listen. Even empty space is not truly empty. Quantum physics says that fields pervade space, fields for electromagnetism, for particles, etc., and they are never completely at rest. Tiny fluctuations are always happening. Particles and antiparticles can briefly appear and annihilate, a restless whisper of creation and destruction even in vacuum. These quantum flits have observable effects. In laboratories, if you place two metal plates extremely close together in a vacuum, certain quantum fluctuations are suppressed between the plates, resulting in a subtle inward push. This is the Casimir effect, a gentle force arising purely from the properties of space. Thus, something as ethereal as the vacuum still has a kind of structure, an underpinning energy that can make its presence known in delicate ways. All these phenomena, relativity's time dilation, gravity's curvature of space, gravitational waves, quantum fluctuations, reveal that space is not a passive void, but an active, structured entity. It bends, it carries vibrations, it foams at microscopic scales. We live in this medium, and we ourselves affect it. When you stand on Earth, you ever so slightly warp space-time around you. When you wave your hand, you send a vanishingly tiny gravitational wave into space. We are usually unaware of these things because their scale is far outside human sensation, but they are always there, the hidden heartbeat of the cosmos. Keep this in mind as we zoom into the human scale. Space is not just a backdrop for our lives. It's intimately involved in everything we do. The rhythm of time we experience, the ticking of clocks, the aging of our cells, is marginally different at the top of a skyscraper versus at its base because of gravitational time dilation. When we measure a length or drive a car, we are moving through space-time that is shaped by Earth's mass and by our velocity. We navigate using satellites that must adjust for the warping of time in space. Even our sense of here and now is relative. Two events that occur simultaneously for one observer might not be simultaneous for another moving relative to them. Space-time underlies it all, knitting together the where and when of everything. Now, let us descend from the cosmic and the abstract to the realm of the concrete and the personal. Let us talk about you, tiny thinking beings who have begun to step off your world and venture into me, into space. On Earth, beneath the dome of your sky, early humans looked up and saw my tapestry of lights without truly understanding what they were, yet they felt wonder and curiosity. They told stories about the patterns in the sky, stories of gods, animals, and heroes placed among the stars. The night sky was a source of guidance and mystery. The motions of the sun, moon, and constellations became the basis for calendars, navigation, and myth. In those ancient days, space was the realm of the divine or the unknown. The idea of traversing it was beyond imagination, but the yearning to know it was already there. As the centuries passed, you learned to chart the heavens with science and reason. You found that Earth is not the center of all things, but a planet orbiting one star among billions. You realized that the stars are distant suns, that the hazy band of the Milky Way is the collective glow of myriad stars, too faint to see individually. Your conception of the cosmos expanded. With it, so did your ambitions. The sky went from being a fixed celestial sphere to a deep ocean beckoning exploration. Eventually, in the mid-20th century of your common era, you took your first tentative steps off your planet. I remember the moment, in the year you call 1961, when a human first left the cradle of Earth's atmosphere and entered orbit. For the first time, a creature of Earth was in open space, encased in a fragile metal sphere, falling freely around the planet. The sky turned from blue to black, and the ground below curved into a breathtaking panorama. Not long after, you sent two of your kind to walk upon the moon, the first footsteps on another world. In bulky suits, within my airless expanse, they bounced across the grey lunar dust. Explorers in a place where no life had ever been. They found the moon a silent, stark world, with my vacuum pressing on them at every turn. The lunar sky was a pure black void, even in broad daylight, spangled with unblinking stars, a sight impossible under Earth's bright blue atmosphere, and a constant reminder that they were on an island of rock amid a sea of emptiness. They looked up and saw Earth rising above the moon's horizon, a fragile blue and white marble hanging in the dark, breathtaking and singular. Many who saw those images felt a profound unity and poignancy. The entire human species, all of history and life and color, contained on that tiny sphere against the infinite night. When those astronauts came home, they struggled to put into words what they had experienced. One of them described the Earth as one shining pearl against an endless void of indescribable beauty. They spoke of the overview effect, a cognitive shift that comes from seeing Earth from space. Borders vanish, petty differences dwindle. The atmosphere reveals itself as a thin, glowing halo, so tenuous, so easily disrupted. Many astronauts returned with a new sense of responsibility toward our planet, saying that, from space, it was clear that all of us are in this together, riding on this tiny spaceship through the emptiness. But leaving Earth also exposed humans directly to the harshness of my domain. Space is hostile to life as you know it. Beyond the cocoon of your atmosphere, the sun's unfiltered radiation is dangerous, and cosmic rays, high-energy particles from faraway explosions, zip through your cells. There is no air to breathe, no pressure. Step outside a spacecraft without protection, and you would lose consciousness in seconds and perish shortly after. The stark sunlight can heat a surface to boiling, while the shade can be hundreds of degrees below freezing. In orbit around Earth, the first travelers found that even simple things became strange. With no up or down, their inner ears were confused. Many felt space-sick until their brains adapted. They watched droplets of water float like jewels and had to learn to swallow and move in microgravity. Over days and weeks in zero gravity, their muscles weakened, no need to fight gravity, and their bones began to lose calcium. Blood and fluids flowed upward into the head, causing puffy faces and sometimes affecting eyesight. Their hearts, not having to pump blood uphill from the legs, began to slow and shrink. Some astronauts reported strange dreams, perhaps influenced by the unusual environment, and many had difficulty sleeping while floating weightless. They had to tether themselves to a bed or sleeping bag to avoid drifting about. Yet humans adapted impressively. They found ways to exercise vigorously in orbit, running on treadmills with bungee cords to simulate weight, or straining against resistance machines to stave off muscle and bone loss. They learned to schedule their work and rest under an artificial cycle of day and night, since, in low Earth orbit, the sun rises and sets every 90 minutes, which would thoroughly scramble natural rhythms without careful planning. They also marveled at things impossible on Earth: the ability to float freely, to lift heavy objects with a fingertip, to fly with the push of a toe. There was a childlike joy in microgravity that many expressed, a dream of flying realized, dancing through a habitat like Peter Pan. Above all, they were struck by the view of Earth. Orbiting roughly 400 kilometers above the surface, astronauts could see entire weather systems, the outlines of continents, the glow of city lights at night. They saw lightning flicker in clouds from above, and the dancing curtains of the aurora australis and borealis, caused by solar particles interacting with Earth's magnetic field, from a front row seat. The thinness of the atmosphere amazed them. The life-sustaining air was just a fragile film hugging the planet. One astronaut said he could blot out the whole Earth with his thumb held at arm's length, an astonishing perspective on how small our world really is. A few humans went further, journeying to the moon. Only a couple dozen have seen the entire Earth shrinking into the distance, becoming a tiny orb in the sky. On the moon's airless surface, they worked and explored under a black sky with no atmosphere to scatter sunlight. Every sound they made came only through their suits. The lunar landscape itself was deathly silent. Hammering a metal core sample tube into the ground, they said, was like hitting a pillow. There was no clang, no noise except what conducted through their gloves. Some said they felt utterly alone, yet in awe, standing on our cratered satellite with the universe staring them in the face. They left footprints that will remain for millions of years in the inert lunar dust, a testament that life from Earth once came that far. When they returned, they carried moon rocks, new knowledge of our nearest neighbor, and a changed perspective looking outward. Those moon journeys are now decades past. No human has been beyond low Earth orbit since the early 1970s. But the legacy of that era of exploration lives on, in satellites, in space stations, in dreams of future missions. Even without humans aboard, your presence has extended far into space. Robotic explorers have visited all the planets of the solar system, and even departed it. In 1977, two small probes, Voyager 1 and Voyager 2, were launched on grand tours of the outer planets. They revealed wonders: volcanoes on Jupiter's moon Io, methane seas on Saturn's moon Titan, the bluish ice giant worlds Uranus and Neptune with their own rings and moons. After their planetary missions, the Voyagers continued outward. Decades later, they became the first human-made objects to enter interstellar space, beyond the heliosphere, the sun's protective bubble of solar wind. They carry golden phonograph records etched with sounds and images of Earth, music, greetings in many languages, the laughter of children, a mother's kiss, a whale's song. These were a message in a bottle, cast into the cosmic ocean with hope and goodwill, on the chance that someday, somewhere, someone might find them. Now those silent ambassadors drift in the starry void, under the light of no sun, journeying for perhaps billions of years through my darkness, each carrying a piece of Earth's story. Thus, even as human feet currently tread only on Earth, and their past prints rest on the moon, your reach extends much farther. Your eyes, through powerful telescopes, have seen galaxies billions of light years away. Your ears, through radio dishes, have heard the faint signals of pulsars and the echo of the Big Bang. Your robotic emissaries roam Mars, have landed on Venus and Titan, have skimmed past Pluto and comet nuclei. In a way, your tools are your extended senses, making you a multiplanetary and even interstellar species in terms of awareness, if not yet in body. Living in space, even near Earth, has taught you much about the effects of my environment. Your body's evolved in the gentle gravity and thick air of Earth, and in the protective cocoon of its magnetic field. Out here, you face microgravity, radiation, and isolation, and you have shown you can face them. Astronauts have spent up to a year continuously in orbit aboard your space stations, conducting science and maintaining complex life support systems in a place utterly inhospitable outside their thin metal shell. They grow plants in microgravity. They study how fluids behave, forming spheres that float rather than puddles. They examine how the lack of weight affects their own physiology. Each day, they watch the Earth spin below, 16 sunrises and sunsets every 24 hours, a constant reminder of how fast they're moving. 28,000 kilometers, 10 times a rifle bullet's speed, and how connected day and night and the passage of time truly are to the turning of their home planet. The psychological challenge has been significant as well. Those who venture into space must cope with confinement, distance from loved ones, and the ever-present awareness that outside their hatch lies lethal vacuum. Some compare it to sailors in a submarine or researchers wintering over in Antarctica, but space adds an extra layer of remoteness. In the quiet moments, peering out a window at the endless stars, an astronaut can feel an overwhelming solitude, being literally not on Earth. But they can also feel an unparalleled unity with Earth. Seeing it whole, they understand viscerally that it is one world, one home. Many astronauts come back with what they call a planetary perspective, deeply concerned about the environment and peace. One moonwalker famously said that from the moon, Earth looked like a tiny garden that must be cared for, and he felt upset that nations were divided. From space, such divisions are nowhere to be seen. Even more distant travel lies ahead, should humanity choose. Plans are drawn for voyages to Mars, to asteroids, perhaps one day to the moons of Jupiter and beyond. With each step outward, new challenges of distance and duration arise. A trip to Mars would take months each way, exposing travelers to long periods in microgravity and higher doses of cosmic radiation. They will need to be self-reliant to a degree no previous explorers have been, because Earth will be just a pale star in their sky, and help, or rescue, essentially unavailable. Yet, driven by curiosity and the spirit of adventure, it seems likely that eventually humans will try, setting footsteps on the dusty red deserts of Mars just as they did on the Moon. For billions of years, space, surrounded Earth without any life venturing forth. Now, a bold and clever species has begun to dip its toes into my sea. In their short decades of spaceflight, they have learned much about me, and in turn, I have tested them in every way. I have made their bones ache, their hearts strain, their technology struggle against unforgiving conditions, and I have rewarded them with perspectives that redefine them, knowledge that enriches them, and achievements that inspire them. We are at the dawn of a new chapter, one where a living planet starts reaching into the wider cosmos. I, space, welcome you, even as I challenge you. There is room for all of us in this great expanse. Space is not always calm and passive. I have my weather and tempests too. You do not feel a breeze in the vacuum, but on cosmic scales, stars and galaxies can create storms of particles and fields that sweep through the solar system and beyond. Chief among these is your Sun, a wondrously dynamic star whose behavior can have immediate effects on Earth and its environs. The Sun continually emits the solar wind, a stream of charged particles, electrons and protons, flowing outward at hundreds of kilometers per second. This solar wind is like a faint breath filling the solar system, creating an elongated bubble in the galaxy called the heliosphere. Earth is inside this bubble and is largely protected from interstellar space. Yet the solar wind itself interacts with Earth. Earth's magnetic field stands as a shield, carving out a cavity in the solar wind called the magnetosphere. As the solar wind flows around this magnetic bubble, it carries with it the Sun's magnetic field lines, which can reconnect with Earth's at the poles and funnel particles down into the atmosphere. The Sun's output is not steady. It has an approximately 11-year cycle of activity. At solar minimum, the Sun's face may be blank and peaceful. At solar maximum, it is freckled with sunspots, cooler, magnetically intense regions, and it may unleash dramatic solar flares and coronal mass ejections, CMEs. A solar flare is a sudden flash of radiation across the spectrum, including X-rays and UV, born from magnetic energy release. If the Sun is a serene orb most of the time, a flare is like a spontaneous wildfire on its surface, outshining the entire star for minutes in high-energy rays. When aimed toward Earth, strong flares can disrupt ionospheric conditions, causing radio blackouts and affecting communication and GPS satellites. Even more impactful are CMEs, bubbles of plasma and magnetic field that the Sun sometimes burps out, containing billions of tons of ionized gas hurled at millions of kilometers per hour. When a CME is directed toward Earth, it typically takes a couple of days to arrive. As it plows into Earth's magnetosphere, it compresses the sunward side of our magnetic field and distorts the night side into a long tail. This sudden jolt energizes particles trapped in Earth's magnetic field and can send some spiraling down into the upper atmosphere. What follows is one of the most beautiful sights nature offers, the auroras. In the polar skies, usually invisible energy and particles announce themselves in cascades of color. Electrons from the magnetosphere, guided by Earth's field lines, slam into molecules of air roughly 100–300 kilometers above the ground. These collisions excite atoms, mainly oxygen and nitrogen, which then release light as they return to their ground state. Curtains of green, touches of red and violet, even swirling blues dance across the polar heavens. They sway and undulate as geomagnetic storms shift the patterns of electric currents above. On particularly strong storms, auroras that normally stay near the Arctic or Antarctic Circle can spill towards lower latitudes, lighting up skies over Canada, northern Europe, or the southern tips of Australia and New Zealand. People stand transfixed at these auroral displays, often not realizing the intimate connection they have to the Sun's unruly behavior and the often invisible web of magnetism that links Earth to its star. However, what is enchanting to the eye can be disruptive to technology. The same geomagnetic storms that make auroras can induce electric currents in long conductors on the ground, power lines, pipelines, undersea cables. In 1989, a powerful solar storm triggered currents that overloaded transformers in Quebec, Canada, causing a province-wide blackout in the span of minutes. And the historical record tells of an even greater event. The Carrington event of 1859, a solar superstorm so intense that telegraph equipment sparked and caught fire, and auroras were seen near the equator. Were such a storm to occur today, it could severely damage satellites, knock out power grids globally, and disrupt radio communications and navigation for days or weeks. It's a sobering thought that even here on Earth's surface, seemingly far from the sun, our technologically dependent civilization is vulnerable to the sun's whims. In space, the effects are more direct. Satellites can be bombarded by solar energetic particles, accelerated by flares and shocks from CMEs. These particles can fry delicate electronics or cause temporary outages. Solar storms heat and expand Earth's upper atmosphere, increasing drag on low-orbiting satellites and causing them to slowly fall from orbit sooner than expected. Astronauts on the International Space Station must at times retreat to more shielded parts of their habitat during intense solar particle events to minimize radiation exposure that could increase their risk of cancer or acute radiation sickness. Future explorers venturing beyond Earth's magnetosphere, say to the Moon or Mars, will be even more exposed. Part of planning those missions is figuring out how to provide adequate shielding or quick shelter if the sun erupts. Then there are the cosmic rays that permeate space from beyond the solar system. These are particles, mostly protons, some heavier nuclei, that are accelerated to near light speed by distant supernova explosions and other violent astrophysical events in the galaxy. They zip through the galaxy and our solar system, and while Earth's atmosphere and magnetosphere protect those on the ground, astronauts in orbit or on the way to Mars are less shielded. Cosmic rays slice through cells, breaking DNA, contributing to long-term health risks. Spacefarers essentially receive higher doses of radiation equivalent to many X-rays or CT scans over time, and it's one of the major limiting factors for how long humans can safely stay in deep space. Even our electronics feel it. Cosmic rays can flip bits in computer memory or gradually damage solar panels. Earth's magnetic field and atmosphere together form a precious force field that makes surface life possible. Mars, by contrast, lost its global magnetic field billions of years ago, and the solar wind has since stripped away much of Mars's atmosphere. It's a reminder that the gentle conditions you enjoy on Earth, a temperate climate, a shield from cosmic hazards, are not universal. They are an exquisite balance, one that space weather can disturb, but, thanks to Earth's defenses, usually not destroy. From a broader perspective, space weather connects Earth to the sun in an intimate dance. Every aurora is a visual song played by the solar wind on Earth's magnetic harp. Every satellite glitch or radio blackout is a reminder that we are not isolated. We live within the sun's outer atmosphere, influenced by its moods. We think of space as cold silence, yet here is a direct chain of cause and effect linking a storm on the sun's surface to the flicker of power grids or the sparkle of northern lights on Earth. It is a beautiful and humbling interconnectedness. Standing under the night sky during a strong aurora, one can imagine the lines of magnetic force stretching down from space, painting the sky with solar wind pigments. In those moments, space doesn't feel so distant after all. It is interacting with your world, showing that the boundary between Earth and space is porous and alive. We have spoken of the visible and the tangible, but much of my content is hidden. Most of the structure I host is shaped by something you cannot see, dark matter. This mysterious form of matter neither emits nor absorbs light. It doesn't glow, doesn't reflect, doesn't interact with electromagnetism at all. It announces itself only through gravity, yet it is everywhere, and it outweighs the normal matter by a factor of about 5 to 1. Galaxies are like icebergs. The stars and gas you detect are merely the tip, while a huge mass of dark matter forms the bulk below the surface of visibility. Every galaxy is embedded in a vast halo of dark matter that extends well beyond its visible edges. In the Milky Way, for instance, stars orbit in the disk out to maybe 50,000 light-years, but the dark matter halo stretches hundreds of thousands of light-years, enveloping the galaxy and gradually fading into the intergalactic medium. This halo holds the galaxy together with its gravity. In the 1970s, astronomer Vera Rubin measured how fast stars orbit in the outer parts of spiral galaxies and found, surprisingly, that they were moving as fast as stars in the inner regions. According to the visible mass alone, stars at the edges should have been moving more slowly, or else fly off into space, as the outer planets of the solar system move slower than the inner ones. Instead, the outer stars were zipping along as if there was some additional gravitational glue holding them in orbit. The conclusion was unavoidable. A staggering amount of unseen mass lurks in and around each galaxy, providing the gravitational pull to keep those fast-moving stars bound. Other evidence accumulated. Clusters of galaxies behaved as though significantly more mass was present than the light indicated. In the 1930s, Fritz Zwicky had already noticed this in the Coma cluster. Galaxies were moving too fast to be held by the observable mass. Gravitational lensing maps, the bending of light by mass, of clusters today show the same. The light from distant background galaxies is distorted in patterns that reveal far more mass than we can directly see, and these lensing-based mass maps align with the dark matter hypothesis. It is humbling. Without dark matter, the universe's large-scale structure would look very different. Galaxies might not have formed so quickly. Clusters would not hang together. You, who live on Earth, owe your existence in part to dark matter. Without its extra gravity in the infant universe, pulling matter into clumps, the gas might have remained too uniform for stars and galaxies to form when they did. Dark matter was the cosmic scaffolding, the unseen hand that helped mold the bright world we can see. What is dark matter truly? This question remains one of the greatest mysteries. You have given it a name, but not yet found its identity. It could be a new kind of fundamental particle that interacts only weakly with normal matter, perhaps a relic of the Big Bang that froze out with the right properties to avoid clumping at small scales. Since we don't see dark matter form smaller structures like stars, it seems to stay diffuse on subgalactic scales. Generations of scientists have built detectors in deep mines and sent instruments into space to search for a whisper of interaction between dark matter and regular atoms, so far to no avail. It's elusive, slipping through detectors like a ghost. Alternatively, perhaps our understanding of gravity needs revision for extremely low accelerations or large scales. An idea that some theories, MOND for modified Newtonian dynamics, or other modified gravity theories, propose. But those struggles to explain all observations as cleanly as a universe full of dark matter. The prevailing view remains that dark matter is some kind of particle or substance outside the familiar roster, not protons, neutrons, or electrons, not photons or neutrinos, but something else entirely. Around the world, experiments continue to listen for the faintest knock of dark matter interacting, but so far, it remains truly dark. And yet, while dark matter itself is obscure, its effects on the cosmos are clear. Galaxies rotate as they do because of it. Clusters remain bound because of it. The cosmic web's very existence was shepherded by it. In the early universe, dark matter clumped under gravity even while normal matter was kept apart by radiation pressure. Dark matter formed a loose framework of overdensities, like invisible scaffolding. When the universe cooled enough, normal matter fell into those dark matter potential wells, lighting them up with stars and galaxies. Thus, the cosmic web of galaxies we mapped earlier essentially traces the underlying dark matter distribution. We see the bright filaments, but the true bulk, a hidden lattice of dark matter, underpins them. It's a bit like looking at a lit city at night from an airplane. You see the streetlights but not the roads. Yet you infer the roads connect the lights, making a network. Dark matter are the roads, galaxies, the streetlights. We infer the dark skeleton by the galaxy's placement and motions. It's humbling to realize how much of the universe's content is invisible to our senses. For millennia, humans thought what they saw was the entire universe. Only in the last century did you realize that even the galaxy is but one of countless others. And only in the past few decades have you accepted that the majority of matter is of an unknown, unseen form. The cosmic story keeps teaching the same lesson. There is more than meets the eye. Reality is not confined to the narrow band accessible to human perception or even human instrumentation. And yet, by extending your inquiry, you have managed to illuminate some of that darkness, mapping dark matter's distribution through its gravitational effects, if not yet touching its essence. So here we are, a universe illuminated by the brilliance of stars and galaxies, structured by the gravity of dark matter, and driven in its expansion by the subtle pressure of dark energy. A tapestry woven of the known and the unknown. We have traversed eons and distances, and our journey has explored the grand scale of existence. Now we drift toward the horizon of the far future to consider how the story might continue. What is the ultimate fate of all this? The galaxies, the stars, the very space and time we inhabit. It is an existential question, both scientific and philosophical. If the current understanding holds, with dark energy continuing to accelerate the expansion, the future looks lonely. Over extremely long times, dark energy will push galaxies not bound to us beyond our observational reach. Trillions of years from now, observers in what will by then be the merged Milky Way Andromeda galaxy, sometimes called Milkomeda, might see no other galaxies at all, only the faint glow of their own stars amid darkness. The rest of the universe will have slipped away. But long before that ultimate isolation, other changes will occur. Star formation will gradually cease. Galaxies like ours still form new stars today from reserves of gas, but those reserves are finite. Perhaps in 100 trillion years, that's 10 or 14 years, an almost unimaginably large span, about 10,000 times the current age of the universe, the supply of cold gas needed to birth stars will be exhausted or locked in stellar remnants. The very last stars to form will likely be small, cool red dwarfs, winking on feebly in a universe that has grown quiet and dim. Imagine that epoch. A universe ages and weary. In a galaxy like Milkomeda, there would be few bright stars left, mostly long-lived red and orange dwarfs, because the big blue-white stars died out eons prior. If a planet existed around one of those last-born red dwarfs in the far future, its night sky would be nearly black. Maybe a handful of neighboring red stars would dot the darkness, but the majestic band of the Milky Way would be faded and thin. The globular clusters would have dispersed, and the galaxy's core might be dark, drained of fuel and activity. Our hypothetical far future observers might have no way to know that once the sky was full of billions of galaxies, they might only see the ghosts of a few. As time marches on, existing stars will die one by one. The massive stars go first, of course, in mere millions of years, long gone by the time the universe is a few billion years old. Sun-like stars live longer, billions or tens of billions of years, becoming red giants and then shedding their outer layers to leave white dwarfs behind. Red dwarf stars are the slowest burners. Some can shine for trillions of years. Eventually, though, even the red dwarfs will exhaust their hydrogen. They lack the mass to become giants. Instead, they'll simply fade to a white dwarf state directly, or cool into a dim, infrared object sometimes called a black dwarf, though none of those exist yet, since even the universe isn't old enough for any star to have cooled that much. Gravity will also gradually reshape the galaxy. Over very long timescales, through a process called dynamic relaxation, stars will scatter, and some will be ejected from the galaxy, while others migrate inward. Spiral structures and disks will no longer be maintained once fresh gas supply stops and interactions cease. Galaxies may settle into large spherical collections of stars if they haven't merged into something like an elliptical already. At some point, perhaps around 10 or 19 to 10 to 20 years from now, 10 quintillion years, the occasional close encounters between stellar remnants will cause many of them to be thrown out of galaxies. The galaxy's dark matter halo will also continue to provide gravity, but without new matter, infall, or gas, the structure will diffuse. The universe will enter the so-called degenerate era, dominated not by shining stars, but by the corpses of stars, white dwarfs, neutron stars, and black holes, along with low-mass stars slowly cooling. Picture a galaxy in the degenerate era. It's a vast graveyard in space. White dwarf stars, once the hot cores of sun-like stars, cool and fade from white to yellow, to red to black, over trillions upon trillions of years, eventually becoming cold, dark spheres of electron-degenerate matter. Neutron stars, those city-size leftovers of supernovae, also cool and remain as silent, invisible husks. Planets, if any still orbit, receive no light or heat except perhaps the faint glow of a cooling white dwarf. A planet in this era might be circling a dark star under a pitch-black sky, occasionally perturbed by the faint gravity of a passing remnant star. If protons are fundamentally unstable, a possibility in some grand unified theories, then on timescales of 10^34 years or more, even matter itself may begin to disintegrate. Atoms of iron or any nucleus might spontaneously decay into lighter particles, and those into radiation. If this is true, then solid matter will literally evaporate given enough time. The mountains, the planets, the remnants of stars, everything made of baryonic matter, would slowly turn to a mist of subatomic particles and then to photons and leptons. If proton decay is not real, then those white dwarf and neutron star remnants can persist far longer, effectively forever, unless disrupted by collisions or eaten by black holes. But collisions will eventually happen too, given enough time. The black hole era would follow. Over unimaginably long spans, more and more mass will fall into black holes, either through occasional encounters or as remaining gas is accreted. Stellar remnants might crash into each other or into black holes, consolidating mass. The universe could reach a state where most mass that remains is locked inside black holes, ranging from small ones formed from collisions to the giant supermassive black holes that long ago lurked at the centers of galaxies. These black holes might merge with each other as well, as wandering ones occasionally meet. Eventually, perhaps only great black holes are left, scattered sparsely through an ever-expanding, dark cosmos. Yet even black holes are not immortal. Stephen Hawking theorized that black holes slowly evaporate via Hawking radiation. Quantum effects cause them to emit particles and lose mass over time. The larger the black hole, the colder and slower this process. But given sufficient trillions upon trillions of years, even the biggest black holes will evaporate. A black hole of a few solar masses might vanish in 10^67 years. The supermassive ones might take 100 years or more, but even they are not truly permanent if Hawking's theory is correct. As they evaporate, they will briefly glow more brightly. Small black holes radiate more vigorously at the end. The final stages of a black hole's life would be a burst of particles and high-energy photons, like the dying gasp of something that once was pure darkness. After the last black hole evaporates, the universe enters the dark era. No organized masses remain, only elementary particles and photons, stretched thin and cold. The expansion by then will have carried everything so far apart that each particle may rarely, if ever, encounter another. It will be an ever-diluting soup of extremely low-energy radiation, and perhaps some stable particles like electrons, neutrinos, and some relic dark matter particles, if those don't decay. The temperature of the universe will approach absolute zero asymptotically. Time, at that point, loses much of its meaning, for almost nothing happens anymore. The arrow of time, driven by the flow of heat and the progression of events, will effectively be moot, since a near equilibrium of maximum entropy has been reached. It is a state sometimes poetically called heat death, though it is more a heat emptiness, a diffusion into nothingness. In that final darkness, the cosmos will be remarkably simple compared to its current complexity. No shining stars, no swirling galaxies, no structures or life, just a thin haze of particles and energy, uniformly spread and eternally expanding into even more emptiness. The story that began with an almost blinding flash of creation ends in a slow, quiet whisper into silence. This is one path the future might take, according to our best understanding. It assumes dark energy remains a constant presence. If dark energy were to grow in strength over time, a possibility in some speculative models, an even more violent end could await, the so-called Big Rip. In that scenario, in perhaps some tens of billions of years, dark energy's repulsion might increase without bound, ultimately shredding all bound structures. First galaxy clusters, then galaxies, then solar systems would be pulled apart. In the final minutes before the end, even molecules and atoms could be rent asunder by the escalating expansion. Space would overcome every force, ripping apart matter itself. The universe would end in a singular state of all particles separated from each other, a kind of reverse Big Bang, a very big rip. This dramatic finale is considered less likely by most. Current data suggests dark energy behaves like a constant force, but it remains a possibility if we've misjudged dark energy's nature. Conversely, there's the more comforting but currently disfavored possibility that the expansion might one day halt and reverse, a big crunch. If, say, dark energy were to decay or turn attractive, or if it's transient, gravity could reassert itself and cause the universe to recontract. Galaxies would start moving toward each other rather than away. Distant clusters would come rushing back into view. Over billions of years, all galaxies could coalesce. Star formation might spike as gas is squeezed again, and eventually, everything would converge into a hot, dense state, perhaps even leading to another Big Bang-like event, a big bounce. Some cosmological models imagine an endless cycle of universes expanding and contracting, but current observations of accelerating expansion make such a cyclical scenario unlikely, at least in the standard picture. Thus, heat death is the prevailing projection. It's a melancholy vision, and cosmos full of light and life eventually becoming an abyss of eternal night. Yet there's a certain symmetry to it. The cosmos began in a superhot, uniform state that was dark, no structures to cast shadows or make contrast, and quiet, no one to hear anything, and sound couldn't travel then anyway. And it may end in a super-cold, uniform state that is likewise dark and quiet. From silence and stillness, back to silence and stillness. In between, all the drama of stars and galaxies and living beings is like a brief spark flaring in the vast darkness. It's natural to wonder, is that truly the end? Will there be no rebirth, no phoenix from the ashes? Some have speculated about extremely low probability events in the far future, like the spontaneous emergence of a new Big Bang from a random quantum fluctuation, a concept sometimes whimsically referred to as the appearance of a Boltzmann brain, or other fluctuation in an eternity of chaos. But these ideas are speculative and deeply strange, more philosophical musings than testable physics. As far as our physics can say, the story of this universe has a final chapter of nearly infinite length, where not much happens. It's a sobering thought that the vibrant cosmos we take for granted is transient. The stars are a temporary show, but temporary on timescales of trillions or quadrillions of years, durations so large that they dwarf the human experience, and even the span of life on Earth by ridiculous factors. The universe will remain hospitable to life and consciousness for a very, very long time before the truly final era sets in. By then, who knows if intelligence, perhaps descendants of humanity, or other beings on other worlds, will have found a way to escape to other younger universes, or tap into new physics to avoid a slow fade. Or perhaps by then, all that arises in the universe will have long since merged into some collective consciousness or dissipated. That ventures firmly into the realm of the speculative unknown. Yet contemplate once more that distant epoch, the long twilight of the cosmos. It is peaceful in its way. If there were an intelligence that could somehow survive into that dark era, it would see a changeless, silent expanse and could reflect on the beauty that was, like an ancient remembering youth. In that silence, maybe the universe remembers the brilliance it once had. Every star that shone, every life that lived, all the beauty and love and strife, all now dissolved but not forgotten, imprinted in the structure of space-time itself. Perhaps it's a sentimental notion, but one cannot help anthropomorphize. The universe, born in fire, ends in tranquility, as if coming to terms with itself. So here we are, in a bright dot of time, where the universe is full of light and life. We have traced a journey from the primal darkness through blazing creation, the formation of structure, the emergence of consciousness, and onward to an ultimate darkness. What then does it all mean? This is where science meets philosophy and wonder. From the earliest times, you humans have spun myths about the void and the beginnings of the world. Many cultures imagined the world emerging from a primal emptiness or a cosmic egg, a nothingness that was pregnant with potential. In ancient Greek myth, chaos, the gaping emptiness, preceded the birth of the gods and cosmos. In the Bible's Genesis, darkness was upon the face of the deep until the voice of creation said, "Let there be light." Hindu cosmology speaks of Brahman breathing out universes and drawing them in, cycling existence through vast epochs with an infinite divine presence underlying the play of creation and dissolution. These myths and insights share a recognition that the void is not mere absence, it's a womb of being, an origin of everything. Modern science's narrative has a similar arc, a formless, hot, empty state, empty of structure, if not of energy, gave rise to everything we see today. In a way, the ancient intuition that the universe came from a kind of nothingness was eerily prescient. Likewise, thinkers through the ages debated what space is. Aristotle believed there was no true vacuum, that nature abhorred an absolute void. To him, space was just the relative arrangement of objects. Centuries later, Newton conceived of space as an absolute stage, an unchanging grid on which physics played out. Leibniz countered that space is only a system of relations among objects. If you removed the objects, space had no meaning. The argument was abstract, until Einstein's relativity delivered a surprise. Space and time form a dynamic entity that interacts with matter and energy. Space-time is not a rigid stage, but can stretch, shrink, and convey forces. In effect, Einstein threaded the needle between absolutism and relationalism. Space-time has properties and can act on things, so it's not nothing. But it is also influenced by the presence and motion of matter, so it's not an unaffected background. Now, physicists go further, speculating that space-time might emerge from something deeper, perhaps from the entanglement relationships in a quantum system, or that our 3D space might be a holographic projection of information encoded on a distant 2D boundary of the universe. These ideas, highly theoretical, are attempts to unify quantum mechanics and gravity. Whether any are true, they reflect a continuing evolution in thinking. Space is rich and mysterious. It is not a simple void. It has layers and secrets we've only begun to uncover. So, philosophically, what do we make of our place in space? We began as earthbound creatures, terrified of the empty night and filling it with stories. Now we travel a bit into that night, and we fill it with knowledge, yet the wonder remains, if not increases. We found that space is not out there only. It is also intimately here, within us, and all around us always. Consider this. The very atoms in your body are mostly empty space. If you magnified an atom to the size of a cathedral, Its nucleus would be a tiny grain of sand in the center, and the electrons, mere motes, buzzing at the edges. The rest is vacuum, nothingness. You are, by volume, almost entirely space. Solid matter is an illusion of scale. Zoom in and you mostly see void with tiny particles dancing in it. But those particles themselves are just localized excitations of quantum fields filling space. Thus, the space inside your atoms is continuous with the space between the stars. It's all one connected fabric. Space is within you. You are space, in the sense that space forms the majority of your being and the platform for all your particles. Moreover, you do not live at the bottom of a sea of space, as people once thought of air or the ether. You live in space outright. When you stand under the sky, there is no hard ceiling, just a thinning atmosphere that seamlessly becomes space. The cosmos isn't only above the atmosphere, it's at your feet too, in the ground, between molecules. Earth does not separate you from the universe, it carries you through it. There is no real boundary, only gradations of density and force. At night, when you gaze up, you are looking out from inside space, not peering through a window into it. This leads to a profound realization. Space is the universal connector. It is the medium through which everything and everyone is related. The photons that left a distant star and entered your eye traveled through space, bridging the gulfs and connecting that star to your mind. The gravitational field that holds you to Earth extends through space from Earth to you, binding you both. When two people stand apart, what lies between them? Not nothing. Space, filled with air, yes, but even without air, space separates and also connects them. Through that space pass their glances, their words, if no air, then radio waves or light signals, their touch if they reach out across it. Space is the backdrop and also the channel for interaction. No wonder that many spiritual teachings and philosophies emphasize the unity of existence. Physics is echoing that sentiment. At a fundamental level, everything is connected in the fabric of space-time and through fields that span space. Distances can be huge, yes, but connectivity is built in. Now, here on this tiny planet Earth, one form of connectivity has blossomed uniquely: consciousness. We humans, and perhaps other creatures in their own ways, are the universe becoming aware of itself. We literally consist of stardust and space, organized in a very special way that allows us to reflect on what the cosmos is doing. Through our eyes, the universe has seen its own grandeur. Through our instruments, the universe has probed its own depths and measured its age and size. Through our minds, the universe, this vast, expanding, evolving space-time, knows that it exists and can contemplate its origins and its fate. That is a stunning fact. As one astronomer poetically observed, we are a way for the cosmos to know itself. You and I, for I, space, speak through a human voice right now, are intertwined in this act of cosmic self-reflection. This bestows upon us a remarkable significance. From one perspective, meaning might seem absent in the indifferent physical processes of stars and galaxies, but we supply meaning by caring, observing, and understanding. In a universe that might ultimately end in darkness, it is perhaps up to us and other thinking beings to create pockets of meaning and keep the flame of awareness alive as long as possible. For now, the rest of the universe appears silent. Across all those billions of stars and countless galaxies, we have yet to detect the voice of another intelligence. The intergalactic silence is not just the absence of sound, it's the unanswered question of whether anyone else is out there. Are you, we, alone in this vastness? Perhaps life is rare, or advanced civilizations are few and far between. It could also be that the distances are so great that though others exist, Each island of life remains effectively solitary, separated by oceans of space and time. As of this moment, we have no conclusive evidence of any others. This can feel lonely or precious. If indeed no one else is calling out in the cosmic night that we can hear, then the responsibility to be the universe's consciousness, its storytellers, its appreciators, falls largely on us. It makes each life, each culture, each act of understanding unspeakably valuable on the grand stage. If there are others, how wonderful. There are more eyes of the cosmos, more voices in the choir. But until we know, we must assume that we are the universe's only voice, for now. Thus, the duty is ours to cherish and protect the awareness we have found. The cosmos may be mostly empty and uncaring, but we who care make it, in those moments, a cosmos that cares. When one of us reaches out in love or compassion, perhaps that is, in a poetic sense, the universe extending love to itself, for we are part of it. We return then to the perspective from which we started, a person standing perhaps under a starry sky, feeling small but connected. Yes, the stars are unreachable by our hands, but we are made of the same elements. We follow the same physical laws, and through space and light we commune with them. The calm night that seems so still is in fact abuzz with particles and waves your eyes can't see. Radio broadcasts, cosmic rays, neutrinos from the sun passing harmlessly through your body by the billions each second, maybe even gravity waves from distant collisions, softly stretching and compressing you by subatomic distances. You are swimming in a cosmic sea, largely unaware of the subtle currents and tides, but they are there. We end where we began, in stillness and darkness. But now that darkness is filled with meaning, and that stillness with understanding. The space that once seemed like a void is recognized as the very medium that connects us to everything. It is around us and within us, the canvas on which the drama of existence unfolds. I, space, have been your narrator, but also your constant companion. I am the silence between your heartbeats and the expanse in which galaxies swim. I was there at your first breath, and will be there at your last, enfolding you always. You have listened to my story, and thereby woven your own existence into the cosmic tale. When next you step outside on a clear night, pause and feel the depth of the darkness above. Those pinpoints of light are not just decorations on a dome. They are reminders of the vast community of suns that surrounds you in our galaxy and beyond. The darkness itself is not empty. It is full of possibility, home to the invisible forces and fields that sustain you, and to whatever future lies ahead. Know this: you are never lost in space, because space is not an alien void in which you drift. Space is the very fabric that connects you to the universe, and you to your home, and you to yourself. You belong here. You arose naturally from this cosmos, as surely as a wave rises from an ocean. You are a cosmic being, inseparable from the whole. Our journey through space and time, though condensed in mere words, has been epic, but it is only a narration. The real journey is lived by you, every day. You wake up, you go about your life, and all the while you are moving through space at incredible speeds, as Earth orbits the sun, as the sun orbits the galaxy, as the galaxy moves through the expanding universe. You might not feel these motions, but they are there. You live amid the legacy of cosmic events. Every atom in your body was once inside a star or forged in an ancient supernova explosion. When you drink a glass of water, you swallow hydrogen atoms made in the Big Bang itself. When you take a breath, you inhale nitrogen and oxygen that were forged by stars billions of years ago and spread through space to coalesce into Earth's air now. In a very literal way, you carry the universe within you. As our tale ends, let's take comfort and inspiration in that unity. The next time you feel alone or insignificant, remember that you are an integral part of a vast and wondrous universe that has given rise to minds able to ponder it. Space is not out there. It is here. It is everywhere. It is the medium in which we exist. It is the stage, and we are of the stage, made from its materials and subject to its laws, yet able to gaze back at it with understanding. In the grand scheme, stars are born and die, galaxies collide and drift apart, and even space and time themselves evolve. But in you, the universe has something precious: awareness. Through awareness, the cosmos finds meaning. The hydrogen that was created in the first seconds after the Big Bang now courses through your veins as part of water and organic molecules, and is currently thinking about the Big Bang. That is a remarkable self-reflection. You give the universe a way to know itself and to appreciate its own beauty. Without observers, the grandeur of a galaxy or a nebula is wasted, in a sense. Photons stream into the void unseen. With observers, with minds to see and feel, that beauty is recognized. It matters. In us, the universe has opened its eyes and marveled at its own splendor. As you go forward, carry that cosmic perspective with you. Let it temper your quarrels and expand your empathy. Under the light of the stars, remember that we are all travelers together through space and time, infinitesimal in scale, yet infinitely significant to each other. We are the universe's children and its shepherds. And whenever you look up at the night sky and feel that familiar awe, know that in that moment, the universe is looking back at itself through your eyes. In a very real way, you are space, and space is you. The line between out there and in here dissolves when you realize this. Every atom in your body was once beyond the earth, and every atom will return to space in due time. We are threads in the great fabric, momentarily coalesced into thinking flesh. The story of space is, in some sense, the story of everything. It's my story as the cosmos, and it's your story as a human being. From the silent void to the radiant stars, from the gentle blue sky of Earth to the ink-black heavens of the void, from the beginning of time to its distant end, I have tried to share this saga with you. Our saga. Keep it alive. Add your own chapter with your life and curiosity. And when you need perspective, step outside on a clear night, breathe the air filled with ancient atoms, feel the solid ground, born of stardust, beneath you, and look up. In the darkness, find the faint band of the Milky Way if you can, or simply imagine it. Let yourself feel, for a moment, both very small and very large. Small as an individual in a vast arena, but large as a participant in something so grand. That duality is the gift of the cosmic perspective. I will end this narration, but I, the cosmos, space, the universe, continue, and so do you. The medium through which we exist, that binds everything, is all around you. Space is not empty. It's full of our stories. It is the container of history and the cradle of the future. Embrace it, for it is your home. Thank you for listening to my tale. Whenever you feel alone, remember, you are always embraced by me. I am space. I am the darkness between the stars and the light within atoms. I am the distance that separates and the connection that unites. I am the medium of existence itself. And I am always with you, around you, within you, now and forever, the endless stage on which the drama of creation plays. Let us continue the journey together, you a spark of consciousness and I, the expanse that nurtures it, finding meaning in each other. In that partnership, the universe is not cold, it is alive and self-aware. Under the eternal night, on a tiny planet spinning through infinite space, a being understands, at least in part, its place in the grand story. And that is more wondrous than any ending or beginning. The universe has become aware of itself, and in that, a bit of the darkness turns to light. In the beginning,
there was silence, a silence deeper than night, softer than a held breath. Nothing moved, for nothing yet existed that could move. No stars, no galaxies, not even the whisper of a breeze in the dark. In this primordial stillness, before light and time and form, there was only a pregnant pause, an infinite calm awaiting a spark. And then, in that void, something happened. A flash, a burst of unimaginable brightness, and the silence was broken. The universe was born in an eruption of light and energy, a silent explosion that rang with no sound, yet carried the promise of everything to come. From that moment, space unfurled like a new scroll, stretching, expanding, filling with the first hot glow of creation. Still, there was no ear to hear, no eye to see. All was energy and plasma and the slow birth of matter. Yet, as the cosmos burgeoned outward, the silence remained underneath the cosmic symphony, like a bass note holding all melodies, the backdrop of the vast expanding space. Eons passed in wordless majesty. Stars kindled across the darkness, clustered into galaxies, swirled into patterns by gravity's gentle but inexorable hand. Great structures formed, filaments of galaxies and voids larger than anything we can truly imagine. In all of this grandeur, in all the furnace roar of stars and the collisions of galaxies, a profound silence still reigned. It was not an empty silence, but a pregnant one, the silence of a universe in the making, as yet without anyone to witness it. Nebulae blossomed like cosmic flowers, stars lived and died, forging heavy elements in their hearts and scattering them into the void. Planets coalesced around distant suns. Perhaps on countless worlds, oceans pooled and gentle winds blew under alien skies. But for ages, no voice broke the silence, no mind yet asked a question. On one tiny planet, orbiting an ordinary star in an ordinary galaxy, something miraculous stirred. Life. In warm, shallow seas, simple microbes began to live, multiply, and evolve. The silent universe had given rise to tiny living things that could sense and respond. They knew nothing of the larger cosmos, only the immediate instinct to survive. But life grew more complex and daring. It crept onto land, took on myriad forms in oceans and forests. And in time, on that little blue world, consciousness sparked. Creatures emerged who could wonder. They looked up at the night sky with curious eyes. They felt small under the canopy of stars, yet compelled to reach out in thought. From their lips and hearts came the first question: what is all this? Where did it come from, and why? Thus, in a corner of the universe, the great silence birthed a question. It was perhaps the first time the cosmos had been asked to reflect on itself through the very beings made of its dust. In those early questions, uttered around flickering campfires or silently pondered under the wheeling stars, the universe itself found a voice. Through us, the cosmos began to speak and to ask. A strange paradox. Out of the universe's stillness grew minds that would not be still, that hungered to know. The night sky's grandeur made early humans feel both awe and mystery. They saw patterns in the stars and spun stories, sensing perhaps that the darkness was not empty, that there was something vast and eternal out there, beckoning. Who placed the stars in the sky? What lies beyond that glittering curtain? Is the universe around us all there is, or just a piece of something far greater? These questions, simple and profound, were the beginning of our journey. And they have no end. As though space itself were whispering to us, we felt an urge to explore, to seek the limits of what we can see. We learned to build tools, first telescopes of glass and metal, later great observatories, to extend our vision deeper into the silence. With each improvement of our cosmic eyes, the known universe grew. What once was a dome of twinkling lights became an ocean of stars, then countless galaxies, and then structures beyond galaxies. We discovered that the stars are not scattered randomly. They are gathered in immense cities of stars, the galaxies.
each containing billions or trillions of suns. Our own Milky Way is one such city, a flat disk of light arcing across the sky. And beyond it, we found others. Andromeda, the whirlpool shapes of spirals, the blob-like ellipticals, the tiny dwarfs swarming around bigger ones. We realized the universe is composed of these galaxies scattered through space like handfuls of luminous sand tossed into the dark. Through patient observation, we determined the scale of our cosmic neighborhood. Light, that fastest of messengers, takes years to cross the gulfs between stars and millions of years to travel from one galaxy to another. We began to grasp that the lights in the sky were incredibly distant. The deepest images, taken with sensitive instruments, staring for days into what seemed like an empty patch of sky, revealed a staggering sight. Hundreds of galaxies in just a pinprick of darkness. It was like finding a shimmering city on what looked like a blank horizon. Everywhere we point our telescopes, if we look long enough, galaxies appear. The observable universe, the portion we can in principle see, contains at least 2 trillion galaxies, each with billions of stars. These numbers defy imagination. Even as we say them, do we truly understand? Each galaxy, an island of stars, perhaps with planets and wonders of its own, multiplied by trillions. The scale humbles us. We sit on a small planet orbiting one star among those countless, and we realize we are tiny. Our world is a mere grain of sand on an endless beach. As our knowledge expanded, so did our questions. We found that the universe has an edge, but not an edge in space like a wall or boundary we could touch. Rather, a limit in time and light. We call it the observable universe, the region from which light has had time to reach us since the universe began. There may be more beyond, much more, but it lies forever outside our view, hidden behind a horizon of light. Why can't we see beyond? Because the universe has a finite age, about 13.8 billion years since the Big Bang fireball ignited existence as we know it. Light from very distant regions simply hasn't had time to travel to us yet. Imagine being in a vast wilderness at night with a lantern. You see trees around you in the lantern's glow. Beyond a certain distance, the forest is dark, not because it ends there, but because the light hasn't reached those faraway trees. Our cosmic horizon is like that, a sphere of light around us, 46 billion light years in radius, beyond which the universe fades into an unknowable darkness. And yes, that horizon's radius is larger than 13.8 billion light years because space itself has been stretching all the while, carrying distant galaxies further out. We peer out to the edge of what we can see, and it appears like a foggy wall, not a solid barrier, but a limit of clarity. That fog is actually the afterglow of the Big Bang, the cosmic microwave background radiation, faint heat left from the time the universe was a hot, dense plasma. It's as far back as light can show us, a view of the universe when it was only about 380,000 years old, beyond which it was opaque. So here we stand, creatures of stardust and curiosity, staring at the cosmic horizon. We strain to see if beyond that faded glow of the primordial fireball, there might be more, perhaps endless galaxies receding into eternity. We suspect the universe doesn't simply end past what we can see. The evidence whispers that space likely continues far beyond our observational reach. The patterns of temperature in that cosmic afterglow are almost too smooth, too uniform, as if our observable patch is just a tiny piece of a much larger whole. If the cosmos ended just past our horizon, space would likely curve visibly or wrap strangely. Instead, all measurements indicate space is very nearly flat on the largest scales, with no detectable curvature as far as we can tell. This implies either the universe is infinite, stretching on without end, or so vast and curved so gently that we have not yet seen the bend. Most cosmologists lean toward the idea that it might be effectively infinite, or at least extremely large beyond comprehension. If that's true, our observable universe could be a mere grain in an infinite desert of universes. Think about that for a moment. Beyond the furthest galaxy we can see, there may be countless more galaxies, and beyond them more without edge. If space truly goes on forever, then somewhere out there, far beyond the reach of any telescope, other beings might gaze at their night sky and see a patch of galaxies that includes our Milky Way as just a faint smudge. Or perhaps they are so distant that even our whole observable universe is just a tiny part of their view. In an infinite cosmos, possibilities become certainties. Somewhere, the arrangements of matter must repeat. It boggles the mind, but in an infinite expanse, there could be another region so far away that it is identical to our own in content. Another patch of space with galaxies arranged just like ours. Another Earth with someone just like you, reading these very words. This isn't science fiction. It's a logical implication of infinity, although it's practically unobservable and forever beyond our interaction. The idea is dizzying and a bit unsettling. An infinity of other realities just out of reach. Yet it reminds us how limited our perspective is. We sit in our tiny bubble of space-time and see 93 billion light-years across. But that might be like looking through a keyhole and thinking that's the entire world. We simply don't know how far the grand stage extends. The true extent of the universe could be infinite, or the universe might eventually loop back on itself in a grand cosmic curve, like the surface of a sphere, but in 3 dimensions. If space is curved into a finite shape without a boundary, it's conceivable, though unlikely in light of current data, that if we traveled in one direction far enough, billions of light years, we might someday end up back where we started, coming up behind ourselves like a traveler circumnavigating a globe. Some scientists have even speculated about exotic shapes for space. One proposal imagined the universe's shape as a kind of dodecahedron, a 12-faced polyhedron, stitched together in a way that the cosmic microwave background might show repeating patterns. For a time, there were hints in the data, faint patterns that could suggest we were seeing the same regions of space in multiple directions, as if light had wrapped around the universe. But so far, these hints have not solidified into proof. The simplest explanation, flat and potentially infinite, remains most plausible. Yet the shape of the universe, its global geometry and topology, remains one of those great unanswered questions. Is the cosmos infinite or finite? Does it have an overall curvature or a unique topology beyond our horizon? We live suspended between possibilities, unable to step outside the universe to see it from the outside. Standing on the shores of the cosmic ocean, we realize that not only is there a limit to what we can see, but that the universe is astonishingly old and dynamic. The cosmos we observe is not eternal and unchanging. It has a history. The galaxies are flying apart, space itself stretching and carrying them away from each other. When we first discovered in the early 20th century that distant galaxies all seemed to be rushing away, it was as if the universe were breathing out, expanding. Rewinding this expansion with our calculations, we found it all converges back to that fiery beginning, the Big Bang. That was a revelation. Our universe had a birth in time. There was a moment, however brief, when all that we see and all that we cannot see was concentrated in an inconceivably hot, dense state. Before that, we do not know if before even exists in a meaningful sense, since time itself might have begun with the Big Bang. This origin story is derived from solid evidence: the expanding space, the cosmic background radiation, the mix of light elements. Yet it leaves us with profound mysteries. What ignited the Big Bang? What, if anything, came prior? Was it truly the beginning of everything, or just the beginning of our cycle of reality? We humans, naturally curious, push against the curtain of the unknown. We have conjectured many ideas for what set the stage for our universe. Some propose that our Big Bang might have been one of countless others. Perhaps the universe goes through cycles of birth, death, and rebirth, a bouncing cosmos that contracts and then explodes anew, over and over. Others imagine our universe budding off from a parent multiverse, a foam of bubble universes endlessly forming like bubbles in boiling water. each bubble a universe with possibly different properties. In such scenarios, the Big Bang was not the absolute beginning, but simply our bubble's local genesis. Still others invoke the idea of quantum fluctuations. Maybe nothingness is inherently unstable, and a tiny fluctuation could tunnel into creating an entire universe. Our cosmos could have sprung from a quantum event out of a vacuum of some higher reality. These ideas venture far beyond the realm of testable science, at least for now, but they arise naturally from our attempt to answer the question of origins. The truth is, we don't know what caused the Big Bang, or if that concept even makes sense in the absence of time. The very word cause assumes time already exists to allow an effect to follow, and if time began at the Big Bang, asking what came before might be as meaningless as asking what's north of the North Pole. Not knowing, however, does not stop the questions, it fertilizes them. Each mystery begets more wonder. We gaze at the observable universe, at that limit of perception, and wonder, if there are things forever beyond our sight, how can we ever know them? Perhaps we cannot, but we can infer hints. For example, our observable universe seems remarkably uniform in temperature in all directions. Even regions that are so far apart, light couldn't travel between them in the age of the universe to even out the heat. How did opposite ends of the sky agree on the same temperature without being in contact? To solve this puzzle, scientists proposed a radical idea: inflation. In the infant moments of the cosmos, a fraction of a second after the Big Bang, space itself might have blown up exponentially fast. An extreme expansion that took a tiny, uniform region and stretched it so vast that all we see now originated from that same patch. This would explain why distant parts of the sky have the same ancient heat signature. They were once close before inflation shoved them far apart. Inflation neatly accounts for some observed properties, suggesting our whole observable universe was once an infinitesimal speck. But inflation, if true, also dramatically broadens our perspective. That initial tiny region after inflation became huge, far larger than what we now observe. And inflation might not have been a one-time event that ended cleanly everywhere. Many inflation theories predict that inflation might be eternal, still occurring in far-flung regions, continually spawning new bubbles of space that themselves go on to expand and cool, becoming universes in their own right. In this picture, our universe is one bubble among a potentially infinite multiverse. Each bubble might have different physical conditions, different types of particles, even different dimensions or laws. We have no way, at present, to confirm the existence of other universes. They would be beyond our horizon, causally disconnected from us. Yet the theory that predicts them arose from trying to explain things we can see, lending some credence to the concept. The multiverse idea tickles the imagination. It suggests a reality far larger or more varied than anything we can directly detect. If true, the great silence beyond our cosmic horizon might be filled with other universes we will never know, a sobering and exhilarating possibility. Some of those universes could be barren, lifeless expanses where stars never formed. Others might be strange, with physics so alien that atoms as we know them can't exist. And perhaps some might be kindred to our own, with galaxies and stars, maybe even life. Of course, these speculations might forever remain philosophical musings. Without evidence, they remain in the realm of the unknown. But it is astonishing that human minds, products of a single universe, can even conceive of realities beyond it. Our imaginations press outward to the ultimate limits of existence, refusing to accept an end to the story. The cosmos, through us, is pondering what lies beyond itself. Yet, even as we dream of multiverses and infinite space, we must contend with enigmas right here in the observable universe, mysteries woven into the fabric of the cosmos we see. In the late 20th century, as our instruments grew more precise, we encountered one of the most profound. We realized that we understand only a tiny fraction of the cosmic contents. All the stars, planets, galaxies, everything that shines, or that we can detect with any form of electromagnetic radiation, amount to a mere 4 to 5% of the total mass energy of the universe. The rest, the vast majority, is invisible to our eyes and instruments, yet its presence can be felt through gravity. This realization dawned gradually, starting with the way galaxies rotate. We expected, based on the gravity of visible stars and gas, that stars at a galaxy's outskirts would orbit more slowly, just as planets farther from the sun move more slowly, weakened by distance. But to our surprise, we observed that stars in the outer reaches of galaxies were moving just as fast as those closer in. It was as though some extra gravitational force was present, something we couldn't see, holding the outer stars in orbit and preventing them from flinging away. The same unseen influence showed itself in other ways. Clusters of galaxies, huge collections where hundreds of galaxies orbit a common center, were behaving as if they had far more mass than what our telescopes could account for. Light from distant galaxies was found to be distorted and magnified by massive invisible clouds, like a giant lens made of something transparent. All these clues pointed to one conclusion. An unknown form of matter permeates the universe, outweighing normal matter by a factor of about 5. We called it dark matter, not because it's dark like soot, but because it neither emits nor absorbs light. It's utterly invisible, detectable only by its gravity. What is dark matter? We still don't know. It could be some new kind of elementary particle that doesn't interact with light or normal atomic matter except through gravity. Perhaps faint, ghostly particles left over from the Big Bang that pass through Earth and through our bodies by the billions every second without a trace. Experiments deep underground and in particle accelerators are attempting to catch a glimpse of a dark matter particle. But so far, they've only placed limits on what it could be. It's humbling. We have this elegant theory of fundamental particles and forces, the Standard Model, that describes atoms and light and so much else, and yet it doesn't include a particle that can account for dark matter. So either there is physics beyond our current theories, a new particle, a supersymmetric partner, a hidden sector of forces, or, just possibly, our understanding of gravity on large scales might be incomplete, meaning what we attribute to unseen matter could be a subtle shift in how gravity works over vast distances. Most evidence favors actual dark matter substance, because the patterns are hard to explain with modifications of gravity alone. Dark matter is like a shadow universe overlain on the one we see. It formed a cosmic scaffolding in the early universe. Imagine an invisible web, filaments and knots of dark matter, and normal matter fell into its gravitational wells. This process seeded the formation of galaxies and clusters along the dark matter web. In a sense, the luminous structures we observe, galaxies, stars, planets, and us, are arranged on the template that dark matter provided. Yet we cannot directly behold this scaffolding. We map it indirectly by observing how it bends light, gravitational lensing, and how it influences the motions of galaxies. What an irony that most of the universe's mass is invisible to us. We are like fish swimming in water yet not seeing the water, only sensing its currents. The dark matter neither shines nor bumps into atoms in a way we can easily measure. It whispers to us only through gravity, the subtlest of clues. We have given it a name. We hunt for it with detectors in deep mines and in the Large Hadron Collider. And perhaps one day we'll finally hear its voice. Until then, it remains a tantalizing mystery, a vast, unknown sea in which the islands of stars float. As if that weren't enough, an even stranger revelation awaited us. At the turn of the 21st century, astronomers painstakingly measuring the expansion rate of the universe made a shocking discovery. They expected to find that the expansion, slowed by gravity over time, was either coasting gently or perhaps starting to decelerate more strongly if the universe had a lot of matter. Instead, they found that the expansion isn't slowing at all, it's speeding up. The galaxies are not just rushing apart, they're accelerating away from each other, like a driver who, instead of coasting uphill, suddenly floors the gas pedal. This was the last thing anyone expected.
Whatever could be causing this acceleration was not something we could see. It wasn't normal mass, which would attract, not repel. We named this mysterious phenomenon dark energy, a term that is a placeholder for our ignorance. Dark energy seems to make up about 70% of the total energy content of the cosmos, dwarfing even dark matter, which is 25%, leaving ordinary matter as a cosmic afterthought.
What is dark energy? That question cuts to the core of our understanding of physics. One possibility is that dark energy is a property of space itself. In the equations of general relativity, Einstein's theory of gravity that describes how matter and energy tell spacetime how to curve, there is a term, the cosmological constant, which Einstein once introduced and later retracted, thinking it unnecessary. This term corresponds to an inherent energy of empty space, an energy that doesn't dilute as space expands. If space has an innate energy, it would act like a sort of pressure or anti-gravity that pushes things apart. And indeed, this cosmological constant idea fits the observations fairly well. A constant energy density in space that started dominating the universe's dynamics a few billion years ago, causing expansion to accelerate. But why would such a constant exist? And why of that particular magnitude? When physicists try to calculate how much energy empty space should have, based on quantum theory, where even vacuum teams with virtual particles popping in and out, the theoretical value comes out enormously larger, a ghastly mismatch with what we observe. It's one of the worst disagreements between theory and observation ever encountered, signifying we deeply misunderstand something. So perhaps dark energy isn't a simple constant. Maybe it evolves, a dynamic field that changes over time, a concept dubbed quintessence after the fifth element of the ancients. Quintessence would be a new substance or field filling space, one that can vary from place to place or era to era, and whose properties we have yet to determine. Another wild possibility, perhaps our understanding of gravity needs revision at the very largest scales. Maybe, like Newton's laws were superseded by Einstein's relativity might itself be a limiting case of a deeper theory that yields an accelerating cosmos without invoking a mysterious energy. For now, dark energy remains an enigma. It's as if we're children who notice that a top is spinning faster on the tabletop than it should, yet we can't see the hand twisting it. The universe's acceleration is a clue that our cosmic story has a twist, literally a speeding up, and we're in the dark, pun intended, about why. What we do know is that given this acceleration, the future is quite bleak for our view of the cosmos. If dark energy continues to push the expansion, distant galaxies will rush away faster and faster. Far in the future, beyond tens or hundreds of billions of years, other galaxies might recede so far and so fast that their light can no longer reach us. An observer in that far future might see an empty universe, just their own galaxy and nothing else, unaware that other galaxies ever existed. The thought that the rich cosmos we observe is a temporary gift of this epoch is poignant. We happen to live when the universe is young enough that galaxies are still in view. The accelerating expansion means the vast majority of galaxies are slipping beyond reach, like ships sailing over a horizon from which they'll never return. But why this is happening? Why now, and what exactly dark energy is? Those answers elude us. The silence regarding dark energy is profound. We can measure its effects with exquisite precision, yet the cause of those effects remains a whisper from the void. From the grandest scales of the expanding universe, let us turn inward to one of the most fearsome and fascinating objects nature allows: black holes. These are regions where matter has been crushed into such density that the fabric of space-time itself has curled in on itself, creating a pit from which nothing, not even light, can escape. A black hole forms, for example, when a massive star reaches the end of its life. The star's core collapses under its own weight, compressing beyond even atomic structure, beyond anything we can properly imagine, until it becomes an infinitely dense point, a singularity,
wrapped in a spherical cloak of gravity. The boundary of that cloak is called the event horizon. Once you cross that threshold, there is no return. The concept of an event horizon is chilling and intriguing, a one-way membrane in the universe. Outside it, space and time behave normally. Inside, all paths inexorably lead down to the central singularity. It's a point of no return, a cosmic trapdoor. Black holes challenge our understanding of physics at a fundamental level. According to general relativity, the singularity at the center has infinite density and zero volume, a place where the known laws of physics break down completely. This signals that our theories are incomplete. Infinities in equations often mean we're pushing the theory beyond its domain of validity. We need a theory of quantum gravity, combining quantum mechanics with gravity, to fully describe what happens at those extreme densities. But we don't yet have that theory. So inside the black hole, hidden from our view by the horizon, nature keeps her deepest secret. It's as if the universe has places it refuses to show us, where it hides the answers to the final exam of physics. What would it be like to fall into a black hole? Imagine approaching a black hole in a spaceship. From a safe distance, it might actually be quite invisible unless it's feeding on surrounding matter, which can glow brilliantly as it heats up falling in. If it's a solitary black hole, you'd see stars behind it, warped into rings or arcs by its intense gravity, gravitational lensing. As you got closer, the pull on your ship would increase. If the black hole is of stellar mass, the gradient of gravity between your nose and tail is so steep it would stretch you out in a process morbidly named spaghettification. You'd be torn apart before you even reached the horizon. But if it's a supermassive black hole, like the ones at galactic centers, millions of times the mass of the Sun, the tidal forces at the horizon might be mild, since the gravity, while strong, changes more gradually across your body. In that case, you could actually cross the event horizon without immediate destruction, and perhaps without even noticing crossing it, since nothing particularly physical marks that boundary aside from the point of no return property. Once inside, however, all paths lead to the center. Your engines, no matter how powerful, cannot reverse course. Time and space trade roles in a sense. Just as you cannot stop moving forward in time, now you cannot stop moving toward the singularity. According to classical relativity, within a short time, you reach the central singularity and are crushed. Your mass adds to the black hole, your identity lost. But physical intuition rebels. Is information truly destroyed in a black hole? Quantum theory says information about a system's state cannot be lost. At least, that's a principle of quantum mechanics as we understand it. If a black hole simply eats things and then evaporates, we suspect black holes slowly evaporate via Hawking radiation, a faint glow due to quantum effects at the horizon. What happens to the information that fell in? Hawking radiation, as originally conceived, carries no information. It's like heat radiating from a warm object, basically random. If a black hole completely evaporates away, does the information of everything it consumed just vanish from existence? That possibility horrified physicists, as it seemed to violate a sacred tenet of physics: information conservation. This is the famous black hole information paradox. Some think the information is encoded in subtle correlations in the Hawking radiation, so that in principle, if you capture all the radiation, you could reconstruct what fell in. Others have proposed exotic solutions. Perhaps the singularity isn't the ultimate end. Maybe it somehow connects to a new region of spacetime, a budding universe or a white hole, theoretical time-reversed black hole that spits matter out. Some suggest that what we call singularity might be a mischaracterization, and quantum gravity, when understood, will show no infinite crunch, but something like a bounce or a portal. Yet others imagine that black holes might have firewalls at the horizon, blistering zones of quantum energy that destroy information before it even reaches the singularity, thus preserving quantum rules, but at the cost of violating Einstein's predictions of a smooth passage through the horizon.
We just don't know the answer yet. Astonishingly, what was once theoretical musing, we have now seen. In recent years, humanity managed to capture an image, via radio telescopes arrayed across Earth, of a black hole's shadow, essentially the silhouette of the event horizon against the backdrop of hot plasma around it. The first such image, of the supermassive black hole in the galaxy M87, showed a fuzzy donut of light, just as predicted by general relativity. We have also measured gravitational waves, ripples in space-time itself, from black holes colliding, hearing the literal ringing of space-time as they merge. These observations confirm that black holes are real, not just mathematical quirks. They exist in the universe by the dozens, likely by the millions. Our own Milky Way harbors a giant black hole at its core, over 4 million times the mass of the Sun. Stars orbit this invisible monster like comets around a phantom sun. And nearly every galaxy likely has one, with masses from millions to billions of solar masses, shaping the evolution of their host galaxies in ways we're still investigating. So black holes stand as both a triumph of understanding, we predicted them, then observed them, and a frontier of mystery. Their insides remain terra incognita. They force the question of how the very large, gravity and space-time, and the very small, quantum particles, mesh together. To truly know what a singularity is, or what happens at that boundary of physics, we will need a unified theory that marries quantum mechanics with general relativity. It's often said that at a black hole's center, the equations of general relativity yield infinity, meaning the theory throws up its hands. It's as if at that point, the universe is saying, "Here, your current understanding halts. A new understanding must begin." In the same vein, consider the nature of time itself, another profound mystery at the intersection of physics and philosophy. Time is something we all experience intimately, yet when we scrutinize it, it becomes elusive. We feel time flow. Every moment, we sense the now moving inexorably to the next now. We remember a fixed past, we anticipate an unknown future, and we seem trapped in this ever-moving present. But what is time? Physics treats time as a dimension much like space. In relativity, time and space are intertwined as space-time. Just as we can move north-south or east-west, we also move forward in time. But why do we only move in one direction in time, whereas in space, we can turn around? Why is yesterday set in stone and tomorrow so contingent? This one-wayness is called the arrow of time, and it appears most strongly when we consider entropy, the measure of disorder. The second law of thermodynamics says entropy in an isolated system tends to increase. Eggs scramble, but they don't spontaneously unscramble. Smoke disperses from a fire, but never gathers itself back into logs. In short, things tend to move from order to disorder, from concentrated energy to spread out energy. This provides a kind of arrow from a past of lower entropy to a future of higher entropy. Our memories and records are traces of lower entropy states. Perhaps the reason we remember the past and not the future is simply that the past is embedded in those ordered traces, like photographs, fossils, neurons in our brain, whereas the future hasn't left any traces yet. In this view, the arrow of time is a brute fact about initial conditions. The universe started in a very low entropy, highly ordered state. The Big Bang, despite being hot and dense, was actually very uniform, which is a kind of order. As the universe evolves, entropy increases. Stars burn fuel and produce heat, matter clumps and then energy dissipates, etc., thus giving time a direction. But this explanation, while broadly accepted, just pushes the mystery back one step. Why was the entropy low to begin with? Why was the early universe so orderly, laying the groundwork for an arrow of time that would later allow life and memory? We don't know. It might be a fortunate accident, or it might hint at deeper cosmological structure. For instance, in some multiverse scenarios, maybe new universes always start fresh with low entropy as they pinch off, and we naturally find ourselves in one of those. Another puzzle. At the microscopic level, the fundamental laws of physics,
ignoring a subtle detail with certain particle decays, are mostly time-symmetric. They don't care if time runs forward or backward. If you filmed two particles scattering off each other and ran the movie backwards, you'd see a perfectly valid physical process. Yet at the human scale, time's asymmetry is obvious. How do those reconcile? The prevailing view is that the asymmetry isn't in the underlying laws, but in the boundary conditions. Again, that low entropy past. Thus, the flow of time might be emergent, not fundamental. Some scientists even propose that time as we perceive it, a flowing river, is an illusion, a byproduct of our consciousness stringing together events, whereas in reality, all moments might coexist in a block universe. In that block universe picture, the past, present, and future are all equally real, just different coordinates in space-time. And it's only our particular perspective, like a spotlight moving along the timeline, that gives a sense of flow. This interpretation is mind-bending because it means now is not a universal truth, but a subjective one linked to each observer. Relativity already showed that simultaneity is relative. Two events that are simultaneous for you might not be for me if we're moving differently. So in a deep sense, the notion of a global present is tricky. Is time perhaps an emergent phenomenon from something deeper, like entanglement or quantum states? Some cutting-edge ideas suggest time might arise from quantum entanglement patterns, or that our universe's time dimension could have sprung forth from a timeless quantum reality when certain conditions were met. These remain speculative, but they remind us that something as fundamental as time is still not fully understood. Time is at once the most familiar thing and the greatest mystery. We live in time. We cannot step outside it to examine it objectively. That's akin to asking a fish to describe water. It's so ubiquitous that it becomes elusive. We mark time's passage with clocks and calendars, but what we're really measuring is change relative to other change. A second is defined in physics by a certain number of oscillations of a cesium atom's radiation, for example. So time is tied to processes. If nothing changed, would time have meaning? In the vast stillness before the universe, if such a state can even be contemplated, what was time? Or did time begin when change began? The silence of the cosmos extends into the subatomic world as well, where our everyday intuitions falter. Peering into the quantum realm, we found uncertainty and paradox. The building blocks of reality, electrons, photons, and other quantum particles, do not behave like little billiard balls following neat paths. Instead, they exist as fuzzy clouds of possibility, described by a wave function that tells us only the probability of finding them in a particular state. It's as if, at a fundamental level, nature doesn't decide on an outcome until something forces its hand, namely, an observation or interaction that makes the potential become specific. This is encapsulated in Heisenberg's uncertainty principle. One cannot precisely know certain pairs of properties, like position and momentum, at the same time. If you pinpoint a particle's location, its momentum becomes uncertain. If you know its momentum exactly, its location smears out. Nature, it seems, imposes a fundamental limit on how much we can know, or perhaps on how much is decided, even in principle. This isn't a limit of technology, but of principle. It's as though the universe, at fine scales, refuses to give a straight answer, offering instead a spread of possibilities. Consider the famous double-slit experiment. When we send electrons or photons one by one through two narrow slits to a screen, an interference pattern emerges, as if each electron were a wave that went through both slits and interfered with itself. Yet, when we put detectors to see which slit the electron actually went through, the interference disappears. The electron acts like a particle that went through one slit or the other, not both. It's as if the electron exists in a ghostly blend of possibilities, both paths, until we look, and then it chooses one path, retroactively making itself a particle that had gone that way all along. This kind of behavior defies our classical logic, and the universe stays mum on how or why it happens. Various interpretations of quantum mechanics try to make sense of it. Some say the wave function collapse is just fundamental and random. Others propose that each possible outcome actually branches off into a separate reality, the many worlds interpretation, where the electron went through left slit in one branch and right slit in another, and these two branches do not interfere once decoherence, entanglement with environment, has happened. Many worlds offers a wild vision. Every quantum event spawns a new universe, so there is an ever-branching multiverse of possibilities. If true, then at this very moment, innumerable versions of reality are splitting off for every quantum choice. In some, you took a breath a second later than in others. In some, a butterfly flapped its wings, whereas in others it stayed still, and those small differences proliferate. This would be a multiverse of a different kind, not separated by vast distances, but coexisting on top of each other in a higher dimensional quantum space, splitting at each interaction. It's a solution to making quantum mechanics purely deterministic. No randomness, just every outcome happens in some branch. But it means that reality is unimaginably more complex than we perceive. Yet from within one branch, we can never communicate with the others. So how could we ever tell if this is true? The cosmos yields phenomena that invite such bizarre explanations, and then remains silent, leaving us to debate and wonder. Another perplexing quantum phenomenon is entanglement, what Einstein famously called spooky action at a distance. When two particles are entangled, they share a single quantum state. If you separate them across the galaxy and then measure one, instantly the other is affected, or rather, instantly you discover that the outcome on one side is perfectly correlated with the outcome on the other side, as if they were connected. For example, two photons can be entangled in polarization, such that if one is measured to be vertically polarized, the other will always be found horizontally polarized, say the opposite, no matter the distance. It's not that one sends a signal to the other at measurement. As far as we can tell, nothing travels between them, and indeed, if you try to use this for communication, it fails. You can't actually send a message this way. Instead, it's as if the two particles are a single entity described by one combined wave function, and when you collapse it by measuring one, you simultaneously collapse the whole system. This is deeply counterintuitive. It implies the universe has non-local qualities. Parts of the universe far apart can be intimately linked in ways that transcend ordinary space and time relationships. Experiments have confirmed entanglement again and again. It's real. We even have technologies exploiting it, quantum cryptography, for instance. But why the universe allows this deep connectedness, how it fits with our concept of locality, and what it means about the underlying reality, remains mysterious. Some thinkers speculate that perhaps space and time themselves are not fundamental, and entanglement hints at a more basic fabric of reality from which space emerges. Picture that what's fundamental is information or relationships, and what we perceive as space is just a way of organizing those relationships for our macro understanding. In such a view, two entangled particles might be adjacent in the deeper reality, even though in our three-dimensional space they are far apart. Thus their coordination is instantaneous because distance is irrelevant in the underlying layer. This is speculative, but it's an attempt to make sense of what nature is quietly demonstrating to us without explanation. The silence of the quantum world, the lack of an intuitive story from nature about what's really happening, has haunted physicists and philosophers for a century. Richard Feynman once said, "I think I can safely say that nobody understands quantum mechanics." It's a humbling admission that even our best theory, confirmed by experiment to astonishing precision, is something we can use, mathematically, but not fully comprehend in plain language. Is the electron a particle or a wave? The only honest answer, it's something quantum, which has aspects of both, and depending on how we interact with it, it will manifest one aspect or another. It's as if reality at base is described not by the solid objects of our sensory experience, but by ghostly probability clouds and interconnections that defy straightforward description. We've developed a comfortable routine with quantum mechanics. Shut up and calculate, some say. Yet the human spirit itches to truly know, to have a picture, a narrative, something that feels resolved. And so far, the cosmos offers none. Perhaps one day a deeper theory, like a successful quantum gravity theory or a theory of everything, will unify these pictures and give us a new paradigm that makes quantum weirdness feel as natural as sunrise. Until then, we live with a fundamental not knowing at the heart of physics. Our journey through the unknown wouldn't be complete without reflecting on the mysteries that hit closest to home. We've looked outward to the edge of the universe and inward to subatomic realms. But what about life? What about consciousness? These are aspects of the cosmos too. After all, we are part of the universe, made of the same particles and subject to the same laws. In the cosmic perspective, life is a recent phenomenon, blossoming on at least one small world. But is it unique to Earth or common as starlight? This is one of humanity's oldest questions. Are we alone? The Earth teems with life in astonishing variety and tenacity. We find life flourishing in boiling hot vents at the ocean floor, in acidic lakes, in the frozen Antarctic permafrost, and high in the atmosphere. Life, once it gains a foothold, is hardy and adaptive. This gives us hope that life could exist beyond Earth, in niches we once thought too extreme, perhaps in the subsurface oceans of icy moons like Europa, or Enceladus, or in the cloud decks of Venus, or on planets orbiting distant stars. We have now discovered thousands of exoplanets, planets around other suns. Some of these are in the so-called habitable zone, where temperatures might allow liquid water. A few are near Earth size and could be rocky. The sheer number of planets in our galaxy is staggering, likely on the order of 100 billion, roughly one per star on average, and many stars have multiple planets. With billions of galaxies, the number of planets in the observable universe might be more than all the grains of sand on all Earth's beaches. If even a small fraction of those planets are habitable, the number of living worlds could be enormous. And yet, we have not heard a peep. The universe, as far as our searches have detected, is quiet about life beyond Earth. No radio signals from alien civilizations beam through the sky, despite our listening via SETI for decades. No unmistakable technological signatures or visits, despite UFO lore. There's no confirmed evidence of extraterrestrial craft. We see no obvious ruins on Mars or elsewhere in the solar system. This great silence is puzzling. It's termed the Fermi paradox. Given the vastness of the cosmos, and presumably many opportunities for life, why have we not encountered anyone or anything? Where is everybody? Enrico Fermi famously asked. There are many possible answers, none confirmed. Maybe life is common, but intelligent life is exceedingly rare. Perhaps simple microbes abound on many worlds, in the oceans under ice crusts of moons, or beneath the soils of exoplanets. But the evolution of complex multicellular life, and then technological intelligence, is an extremely improbable chain of events. After all, for most of Earth's history, billions of years, life remained single-celled. Only in the last 500 million years did complex organisms proliferate, and only in the last few million did a species arise with intelligence capable of radio telescopes and rockets. Perhaps in many biospheres that step never occurs. Life stays microbial or animalistic, never building cities or machines. Or maybe civilizations do emerge on many planets, but they tend to have short lifespans. They might self-destruct via warfare or environmental collapse. Or perhaps they inevitably transition to some other state, like a virtual reality existence, and lose interest in communicating with the stars. It could even be that a galaxy teems with life and intelligence, but it's largely quiet and inward-looking, and the distances are so vast that communication is difficult. Signals might be rare, or we might not recognize them. Perhaps advanced beings use communication methods we haven't discovered, or maybe they abide by a cosmic etiquette, a prime directive, of not interfering with emerging civilizations like ours. It's also possible we are alone, or at least incredibly rare. Maybe life itself is a freak occurrence, needing such a special convergence of circumstances that Earth might be one of only a handful of places in the whole galaxy or beyond where it happened. Some scientists have suggested that certain unlikely events, like the origin of life from chemistry, or the jump from single cells to complex organisms, or the development of intelligence, might be low-probability flukes. If so, the universe could be mostly sterile, with us as a precious exception, or one of very few. That thought is both exhilarating, we're special, and terrifying, so fragile in the cosmic darkness. If we are rare or alone, it puts a huge responsibility on us to survive, to cherish life, to perhaps spread it. We are searching avidly for answers. Our robots crawl on Mars, drilling into rocks to find traces of past microbes. Our probes have sampled the plumes of Enceladus, shooting water from its subsurface ocean into space, and found organic molecules, tantalizing, though not proof of biology. We're designing missions to Europa and other worlds. And from Earth, or Earth orbit, we are beginning to peek at exoplanet atmospheres. We've detected atmospheres on a few distant planets, and soon next-generation telescopes will try to find signatures of life. For example, an atmosphere rich in oxygen, which on Earth is maintained by life, or weird combinations of gases that scream metabolism at work. It's a challenging task. Exoplanets are tiny and drowned out by their bright stars. But the endeavor is underway. Perhaps in the coming decades or centuries, we'll get our first hint that biology is not unique to Earth. Imagine the day we detect, say, methane and oxygen and water vapor on an Earth-sized planet around a distant star, a combination hard to sustain without life. We will not hear aliens say hello, but we might finally know that the cosmic loneliness is an illusion, that life has filled other ponds in the great rain of creation. Until then, we have only questions and the emptiness between the stars. We've sent out our own signals, radio waves that have leaked from our transmitters for a century, spreading out as a faint bubble. 100 light years in radius, and we've deliberately beamed a few focused messages or carried plaques and golden records on spacecraft like the Voyagers. Those artifacts drift now in the interstellar void, likely to wander for millions of years. Perhaps one day, far future, some alien hand, or appendage or machine, will find our little bottles in the cosmic ocean and know that we existed. But for now, the only confirmed life in the universe that we know of is here, on this pale blue dot. That is a sobering truth. It means every living thing we have ever known, every experience of love, joy, struggle, discovery, all of it, has occurred in a thin film of life on one planet's surface. Life is a delicate chemical flame fighting entropy, and Earth is the oasis that nurtures it in our solar system. This knowledge urges us to protect our world, for if life is rare, losing Earth's biosphere would be an unspeakable tragedy. And if life is common, well, then we have friends yet to meet, and we should keep our planet thriving so that one day we might join a galactic community. Either way, the quest to know if we are alone goes on, intertwined with our own future. And then there is consciousness, the most immediate reality to each of us. For what could be more certain than our own awareness? Yet perhaps the hardest phenomenon to explain in scientific terms. Somehow, in the 13.8 billion year journey from the Big Bang's fire to now, the universe has developed the ability to contemplate itself. Hydrogen atoms coalesced into stars. Stars forged heavier elements. Those elements made planets. On one planet, chemistry begat life. Life grew brains, and now those brains contain minds that experience, question, and create. It sounds like a fairy tale, inert matter becoming sentient, yet it happened, in us, and likely in other creatures too, to varying degrees. Surely many animals are conscious in their own ways, though we humans possess a self-reflective awareness and intellect that sets us somewhat apart. How does mere matter give rise to the feeling of being? How does a collection of neurons, exchanging electrochemical signals, produce the redness of a rose, the taste of chocolate, the pang of sadness, the sense of self? This is often called the hard problem of consciousness, because explaining how the brain processes information, responds to stimuli, or controls the body, the easy problems. Those are difficult, but we can see how to approach them scientifically. But explaining why those processes should be accompanied by an inner subjective experience, why there is something it is like to be you from the inside, that's a different matter. We might map every neuron in your brain and track every spike and chemical, and still be left wondering at what point those physical events create a conscious experience. If a computer simulated your brain perfectly, would that simulation be conscious? Or is there something more than computation needed? Science, by design, deals with third-person observations, measurements of things from the outside. Consciousness is inherently first-person. It's the one thing you can't directly observe about me, nor I about you. I can tell you I feel pain or joy, and you can correlate it with brain activity or behavior, but the feeling itself is private. This gap between objective and subjective has led to philosophical standoffs for centuries. Mind-body problem, dualism versus physicalism, etc. The prevalent scientific view is that consciousness arises from brain activity, that the brain is the generator, or at least the transmitter, of the mind. If so, then consciousness should be explainable in terms of neurons and their interactions, but we haven't cracked how. There are intriguing leads. Certain brain processes correlate strongly with conscious states. For instance, synchronized oscillations in certain frequencies, or specific circuit loops in the cortex and thalamus. The Integrated Information Theory, IIT, suggests that consciousness corresponds to the amount of integrated information a system possesses, a measure noted as FEF. Under IIT, even a simple system might have a tiny bit of consciousness if it has a feedback structure that integrates information. So even a thermostat might have a minuscule glimmer of experience, which is a panpsychist kind of implication. Another theory, Global Workspace Theory, GWT, posits that consciousness is like a global blackboard in the brain, where information gets broadcast to many subsystems. What we experience consciously is the stuff that made it into this global workspace. These theories provide models and prediction, but none yet explains why the global workspace feels like something, or why integrated information should result in an inner life. Some thinkers have ventured that consciousness might be a fundamental property of the universe, like mass or charge, an idea known as panpsychism, the notion that perhaps all matter has some degree of consciousness, and complex systems like brains just amplify or collect it into the vivid awareness we know. This is not a mainstream scientific view, but it arises from the difficulty of explaining consciousness purely as emerging from non-conscious parts. If electrons and neurons are totally devoid of experience, how do a trillion of them together produce experience? Panpsychism answers, maybe electrons, and all particles, have extremely rudimentary proto-consciousness, some intrinsic aspect that is mental, and when arranged in complex ways, these form higher consciousness. It's a wild idea, harking back to ancient philosophies that saw spirit in all things. Whether true or not, it underlines how desperate the attempt to solve consciousness has become, that even such ideas get consideration. Alternatively, maybe consciousness is an emergent phenomenon that will eventually be explained in terms of information processing, but we just haven't found the right concepts yet. After all, concepts like temperature and pressure were once mysterious. How does the jostling of atoms create the feeling of warmth? But kinetic theory explained them. Perhaps one day we'll likewise demystify conscious experience, showing how certain patterns of computation just are the subjective feeling from the inside, similar to how a certain frequency of air vibrations just is the subjective experience of a musical note to an ear and brain. Some neuroscientists suggest that if you had a matrix of interconnected neurons or artificial units replicating the brain's structure, an inner life might spontaneously light up. But verifying that will be tricky, again, because we can't directly measure the consciousness, only infer it from behavior or reported experiences.
For now, consciousness stands as an open question that straddles science, philosophy, and even spirituality. The cosmos has produced self-aware beings. We know this because we are them. But we don't understand the spark that lights up our thoughts. We don't know at what point in evolution consciousness arose. Do fish feel? Do insects? What about single-celled organisms responding to stimuli? Is there a faint glimmer of something it is like to be an amoeba? Does consciousness require a brain, or could an alien form of life, like a network of fungi or even a sufficiently complex machine, be conscious? Could the universe itself be conscious in some way, as some mystics and even a few scientists muse? Not in a simplistic anthropomorphic way, but in a sense that there is a level of awareness associated with the cosmos as a whole, or with fundamental fields. These questions drift at the edges of empiricism. They may not all be answerable, at least not by traditional experiments, yet they matter to us, because consciousness is the lens through which we experience everything else. Without it, we aren't even there to ask the questions.
Let us step back now and look at the tapestry of what we know and what we don't know. The cosmos began, as far as we can tell, in silence and mystery, and that mystery remains at every level we probe. We have learned so much: the age of the universe, the recipe of elements, the existence of cells and DNA, the laws of gravity and electromagnetism, the reality of quantum fields, the genealogy of stars and galaxies, the expansion of space, the evolution of life. Our knowledge has blossomed, an impressive collective achievement for a species of former cave dwellers. And yet, what we don't know overshadows the patch of light we've kindled. The volume of ignorance is an ocean around our island of understanding. It humbles us, but it also excites and motivates us. Each generation has pushed further into that ocean. We often find that answering one question opens several new ones. We learned how stars shine, but that led to questions about stellar evolution and supernova. We discovered other galaxies, but that raised questions about dark matter to explain their motions. We uncovered the expanding universe, which posed the question of what the fate of expansion is and introduced dark energy. We deciphered the code of life, DNA, but then faced the complexity of how genes lead to consciousness. It's like climbing a mountain. Each time you reach a summit, you find a higher peak beyond. Far from being disheartening, this is invigorating. It means the adventure continues, perhaps forever. Consider the nature of space itself. At first glance, space seems like nothing, an empty void, the backdrop for matter. But we've come to see space as something with structure and activity. Einstein's relativity showed that space and time can stretch, bend, and ripple. Gravity, in that theory, isn't a force emanating through space. It is the shape of space and time itself, curved by mass and energy. When you put a heavy object like the sun in space, it dimples the space-time fabric around it, and the Earth orbiting the sun is like a ball rolling around a dent, following curves in space-time. This was a radical shift. Space is not just an inert stage, it's a dynamic actor. Then quantum physics adds another layer. Even a perfect vacuum, completely devoid of particles, isn't truly empty. It seethes with ephemeral phenomena, quantum foam, as some call it. Particles and antiparticles can briefly appear and annihilate. Fields fluctuate constantly at microscopic scales. There is a constant jitter in the vacuum, so much so that the vacuum, paradoxically, contains immense energy if summed. though our inability to tap or see most of that energy is another puzzle. These vacuum fluctuations have real effects. They cause tiny, measurable forces. The Casimir effect, where two close plates have a slight attraction due to altered vacuum modes between them, and contribute to phenomena like the Lamb shift in atomic physics. So the nothingness of space is actually a roiling, boiling brew of potential, the foundation upon which everything rests. Space itself might undergo phase transitions. Some cosmologists speculate that in the very early universe, space was in a different state, with different symmetry between forces, and as it cooled, it crystallized into the form we know, possibly releasing energy that drove inflation. The vacuum today might hide exotic fields, like the Higgs field, which pervades space and gives particles mass, discovered experimentally in 2012. A tangible example that space contains fields with constant values. Dark energy could be the energy of space's vacuum. If space has energy, then a volume of vacuum isn't truly nothing. It's more like a latent something. We're reminded of a line from a poet or sage that silence is not empty, it's full of answers. Similarly, space is not empty. It's full of the answers to questions we've yet to formulate. Yet for all that, when you stand outside on a clear night and look up, space feels like an immense, silent void between the stars. That serene emptiness cradles all of creation. It separates and connects everything. Every breath you take, the molecules were at one time scattered in space before the Earth formed. And after you exhale, given enough time, they may escape Earth and wander the galaxy. Space allows that movement. Space, by its vastness, also ensures that objects can exist without immediately colliding with one another. It grants stability to solar systems and galaxies by giving them room. But is space infinite? Does it go on forever? We addressed that earlier. We're not sure. If it is finite, what lies beyond? Perhaps nothing we can comprehend. Or perhaps our three-dimensional space is embedded in a higher dimensional reality. String theory suggests extra spatial dimensions we don't perceive, perhaps curled up small. Could it be that our space is like the surface of a balloon, and there is a higher dimensional space outside it? If so, that's outside our experience, and possibly forever inaccessible. Or maybe beyond all galaxies, beyond the cosmic horizon, space just continues, with more galaxies ad infinitum. So even space, the very fabric we exist in, holds mysteries. Some researchers think space and time might be emergent from something more fundamental, like quantum entanglement patterns or spin networks in theories of quantum gravity. Imagine if space-time is not the base level of reality, but a kind of approximate large-scale picture that arises from microscopic physics that isn't in space-time at all. This is speculative, but we already have hints that space and time break down at extremely small scales. The Planck scale, around 10 or 35 meters. At that scale, quantum foam might be so wild that the notion of a smooth space-time becomes meaningless. Space might be chunky or erratic, full of baby black holes popping in and out, wormhole connections blinking open and shut, a true quantum chaos. We have no microscope to see that deep. It's far beyond our current or foreseeable technology to probe distances that small directly. But mathematical attempts at quantum gravity, like loop quantum gravity or aspects of string theory, suggest space-time could have an atomic or quantum structure. If so, then asking about the continuity of space or the absolute beginning of time might be like asking where exactly a flowing river ends when it fans into a delta. Up close, the distinctions blur. We cannot now answer if time had a beginning, or if space has an edge, or what space is made of, if anything. But we can marvel at the fact that we, ephemeral beings made of cosmic bits, can even frame such questions. Think of the journey, from silent stillness to swirling galaxies, to starshine on primordial Earth, to life evolving in the oceans, to human minds reaching out with curiosity. We are a way for the universe to know itself. That poetic insight appears literally true. Our senses, our instruments,
extend the universe's ability to perceive. Without conscious observers, would the majesty of the cosmos have any meaning? The galaxies would still dance, the stars would still burn, but there would be no appreciation, no insight, no knowledge. Through us, and maybe through other conscious creatures out there, if they exist, the universe gains the gift of self-awareness. We are the cosmos made conscious, and so we are a small part of the cosmos, looking back at itself and trying to understand. It's as if the universe has sprinkled seeds of awareness within itself, and those seeds, in the form of beings like us, awaken and stare out in wonder, asking questions. We ask about the Big Bang and black holes and quantum foam, but in a sense, the universe is asking those questions through us. Space itself speaks in our questions. The great silence of outer space finds a voice when a scientist in a lab theorizes or an artist at night paints the Milky Way. We feel the mystery, and we respond with curiosity. A fundamentally human trait, perhaps a fundamental cosmic trait expressed through humanity. Where do we go from here? The unknowns beckon us forward. We will keep building better eyes, telescopes to hunt for exoplanet atmospheres, to watch the birth of stars, to glimpse the first galaxies forming not long after the Big Bang. We will keep listening for signs of life or intelligence beyond Earth, refining our methods, maybe sending new messages or probes to nearby stars. We'll continue to smash particles together or devise clever detectors deep underground, hoping to catch whispers of dark matter or new physics. We'll push quantum theory to its limits, perhaps eventually developing quantum computers that might simulate aspects of reality we couldn't before, giving insight into those mysteries. Perhaps one day we'll integrate gravity and quantum mechanics into a single, coherent theory, a momentous achievement that could answer some of those questions, maybe revealing what really happens at a singularity or exactly how space-time emerges. And as we do, new questions will arise. Perhaps solving dark matter and dark energy will lead us to other puzzling phenomena. Perhaps understanding consciousness will open entire new realms of science about subjective experience. There's also a chance that some mysteries remain mysteries, either because they are fundamentally beyond our cognitive reach, or because obtaining the evidence is practically impossible, like a multiverse beyond contact, or what before the Big Bang was, if that concept even applies. But even then, exploring these ideas can enrich us. They make us grapple with the limits of knowledge, with the meaning of reality. Throughout all this, one truth remains. To not know is not a failing, but a feature of our existence. If we knew everything, the universe would lose its allure, its dynamism. Each of us in life starts not knowing, then learns, and in learning, discovers more things we don't know. A child might gaze at the sky and not even know what stars are. Later they learn, but then new layers of mystery unfold. What are stars made of? How did they form? The questions grow with the answers. This is the engine of discovery. Our ignorance is vast, but it is the dark canvas on which we paint our understanding. Imagine if every answer were handed to us complete. We'd have knowledge, but no journey, no adventure. It is the chase, the pursuit of truth, that often gives us purpose and joy. The moment of revelation, eureka, is sweet, but it is earned by the long not knowing that came before. And so, even as we strive for answers, we can find peace and wonder in the open questions. The cosmic mystery isn't something to be sad about. It's something to celebrate. It means we are intimately connected to a universe that is richer and more profound than our current imagination. It means there will always be new horizons to seek, new truths to uncover, or at least ponder. Picture yourself under the night sky again, as in the beginning. The stillness of the air, the silent twinkling of ancient starlight. You feel the immensity above and around you. In that moment, you are aware of a grand ignorance. You don't know what all is out there, or why it exists, or if someone might be looking back. Yet you are also aware of a profound connection.
You are made of this universe's elements, your bones calcium from long-dead stars, your blood carrying iron forged in supernovae. The very act of you wondering ties you to the cosmos. Your questions are like a bridge between your mind and the infinite. Yes, the void is silent, but in our minds, that silence begets a quest. We fill the quiet with our inquiries and our explorations. We send out spacecraft, like extending our senses to the planets and beyond. We smash particles to glimpse creation's most microscopic secrets. We invent mathematics to describe black holes and quantum waves. We contemplate philosophical implications of time and existence. These are our conversations with the cosmos, and though it may not answer in words, it answers in wonders. We find one day a new kind of particle, or see a new kind of galaxy, or decode a new signal, and that is the universe's reply, telling us a little more of its story. Perhaps the universe also answers through our own self-discovery. The more we learn about nature out there, the more we reflect on ourselves. We realize how precious life is, seeing how hostile most of space can be. We see Earth from space, a pale blue dot, and it triggers a global awareness of unity and fragility. We understand that we are but one species among many, on one planet among many, in one galaxy among billions. This perspective can evoke humility and also a sense of fellowship with all existence. In cosmic timescales, human civilization is just a blink, and an individual life not even a flicker of a star. But to us, our lives are everything. They are our personal universe of experience. The big cosmic mysteries often reflect in microcosm in our personal mysteries. We wonder what our purpose is, how our minds work, how to find meaning in the vastness. And the answers are not handed to us. Each person, in a way, lives their own questions and gradually, hopefully, lives into answers. In that, we mirror the cosmos. Each of us begins in the darkness of not knowing, and along the way, we gather light. The process is continuous and perhaps infinite. In the end, after traversing all these wonders, from the birth of the universe to the nature of space, from dark matter to consciousness, we come back to a simple human truth. To not know is to be alive. Our ignorance is not just an absence. It is the driving force that keeps us searching, learning, striving. As long as there are things we don't know, we wake up in the morning with curiosity burning in our hearts. As long as mysteries abound, we have reason to marvel and reason to push boundaries. Imagine a final theory of everything that answers all possible scientific questions. Would curiosity die? Perhaps it would shift inward or to new realms, like creating art or simulated universes. But as long as we retain any sense of wonder, we find new questions. Even if somehow we understood the entire physical workings of the cosmos, we might still ask, why is there something rather than nothing? Or, what is the ultimate meaning of it all? Those questions might never have definitive answers. They're asymptotes we approach but never reach. And so we will always, in some sense, not know, and thus always be reaching, always growing. This endless pursuit is a beautiful thing. It means we are participants in a cosmic story of discovery, not just passive beings. The universe is not a static riddle to solve and be done with. It's a living conversation. Today's unknown will be tomorrow's known, and tomorrow's known will open up another unknown beyond. We stand on a threshold at all times. Behind us is knowledge hard won. Before us, the ocean of mystery. And isn't that what makes life and the cosmos endlessly fascinating? If the universe were small and simple enough for us to easily grasp in totality, it might lose some majesty. Its very unfathomability is part of its grandeur. The cathedral of stars overhead, the equations that describe them, and the equations yet to be written all form a grand, evolving tapestry. We humans are but a tiny thread in that tapestry, yet we can observe the whole pattern and add our own embroidery. Our scientific instruments are like extensions of our senses, giving the universe new ways to look at itself. Our poems, paintings, and music about the stars are the universe expressing beauty through us. We often personify the cosmos in our musings, calling her Mother Nature or envisioning gods in the sky, because deep down we feel that intimate connection, that we and it are one. And indeed, we are not separate from the universe. We are the universe, in the form of conscious living matter. Thus, the questions we ask the universe, we are in a way asking ourselves. And when we find an answer, we are the universe knowing itself a little better. Perhaps that is a kind of purpose we can latch onto, to be the mind of the universe, ever awakening further. If star systems are its body, perhaps civilizations are its mind, flickering on and off in the vast epochs, maybe one day linking up if interstellar travel or communication becomes possible, forming a network of cosmic awareness. Or maybe each remains an isolated island of thought. Either way, in us, the cosmic ocean has evolved eyes and brains that can map its shores and begin to chart its depths. The journey of not knowing to knowing, and then finding even more not knowing, is likely endless. And that is good. It means our descendants, be they human or augmented or AI or something beyond, will always have new frontiers. Just as we looked at moons and said, we'll go there, and did, they might look at other stars or dimensions or layers of reality and find ways to reach or comprehend them. Each answer: the moon is barren, Mars had water, black holes exist, spurs new questions. Could life endure on Europa? Could we terraform Mars? Can we travel through a wormhole? The quest fuels itself. Standing under the cosmic sky, we may feel small, but we are also giant in what we carry. The spark of curiosity, the flame of consciousness. The distances are huge, the mass is immense, the energy is unfathomable. Yet none of those physical things inherently produce meaning. A star doesn't seek meaning. A galaxy doesn't appreciate beauty. But we do. We create meaning by examining the cosmos and by simply living and loving within it. Our unknowing and desire to know give the universe meaning, as much as our capacity for joy and love do. In the stillness of a clear night, if you listen closely, you might imagine you hear the stars whisper. Of course, space is airless and there is no real sound. But there is a metaphorical voice, the voice of wonder that arises in your own mind as you behold the stars. That voice quietly says, there is more, so much more. It invites you to ponder, to go further than those who came before, even if just in thought. It's the same voice that led ancient people to map constellations, that led Copernicus to propose the Earth moves around the sun, that led Einstein to envision riding on a beam of light. It's the cosmos, through the medium of human imagination, urging itself on to greater self-understanding. We do not know if we will ever find all the answers. Probably we won't, because each answer breeds new questions in an endless cycle. But that is the brilliance of it. We are alive in an epoch where mysteries abound, and likely every epoch will be such an epoch. We get to be explorers of the grandest kind. Whether we sail actual ships across space or ships of thought across higher dimensions, we are adventurers. Not knowing is the call to adventure. Curiosity is our compass. Each piece of knowledge hard won is a treasure we carry, but the treasure map always extends further. To be alive is to stand on that shoreline between known and unknown and feel the enticing breeze of mystery. It reminds us that we are part of something far larger than ourselves, and yet we belong. We belong in this universe as naturally as photons and quarks and nebulae. We fit because we evolved here and of it. The atoms in our bodies were forged in stars. When we die, those atoms will return to the Earth, perhaps one day to new living beings, or drift into space to join a new star. We are a transient pattern in a much larger flow, but while the pattern holds, we have the privilege of witnessing and wondering. In that sense, our not knowing is even comforting. It guarantees that the tapestry of existence is rich beyond measure. It means there will always be more to learn, more to experience. The cosmos will never run out of surprise and majesty. We humans sometimes fear the unknown, especially on the personal scale. The unknown future, the unknown outcomes of our choices. But we also thrive on the unknown, turning it into the known bit by bit. The key is to accept that uncertainty is fundamental to life and even to the universe. We will never have absolute certainty about everything, and that's okay. That leaves room for faith, for hope, for creativity. It leaves room for us to make choices. If everything were predetermined and fully known, existence would be like reading a book with no alternate endings, interesting perhaps, but static. With uncertainties, we write our own pages as we go. The great cosmic questions, then, are both scientific and existential. What is the universe? How does it work? Blends into, what does it mean for us? What should we do? There is no single correct answer to that latter part that science can give. But perhaps the very act of seeking answers is part of the meaning. Perhaps the growth of knowledge and consciousness is one of the universe's purposes, if such a word can be used. We often imbue purpose in things that might inherently have none, but maybe that's our role, to create purpose. If the universe was initially without meaning, we give it meaning by caring, by exploring, by marveling. And oh, how marvelous it is! This strange existence, where a primate brain can comprehend the birth of galaxies and the death of stars, where mathematics scribbled on paper can predict black holes, and then the sky shows they're real, where we can read the genetic code that links us to every creature on Earth, and yet still scratch our heads about what consciousness is, or how quantum entanglement actually operates. We solve pieces of the puzzle only to find new pieces beyond the edge. It's like an infinite game, and perhaps that is the secret. Life is an infinite game, where the goal is not to win. You can't, since there's no finish, but to keep playing, to keep the game going. In this game, every new insight is a level up, every new mystery a new quest. Eventually, billions of years from now, our sun will swell into a red giant and scorch the Earth, a reminder that even the local theatre of life has an expiration date. By then, if life from Earth is wise and ambitious, it would have spread out to other stars, preserving and expanding the chain of knowledge and being. The universe will continue to evolve. Galaxies will drift apart. Stars will exhaust their fuel. Trillions of years hence, starlight might wink out as the cosmos grows cold and dark, assuming dark energy doesn't do something even stranger like ripping spacetime itself. But that is an unimaginably distant future. In the meantime, we have an abundance of time and possibilities to savor. And even in that far, cold future, perhaps the descendants of our descendants, or whatever life becomes, will have unlocked deeper truths, maybe manipulating dark matter or energy, maybe tapping zero-point vacuum energy, maybe even creating baby universes to escape into when this one grows old. We can dream far indeed. Whether those dreams come true or not, they highlight our refusal to accept limits without probing them. We always seek a way, an answer, an extension. If the universe is expanding, we figure out how to navigate it. If life is rare, we treasure it and propagate it. If knowledge is hard, we train more minds and build better tools. In the reflective silence at the end of our journey, we return to ourselves, here and now. We think of all we have pondered, a universe with billions of galaxies, mostly unknown, mysterious dark matter and dark energy, sculpting fate, black holes challenging our physics, time flowing irreversibly from an ordered dawn, quantum particles dancing an unpredictable dance, countless stars with unknown planets and maybe unknown life, our own fragile existence with a mind that defies full understanding. It's a lot to hold in one head. So we breathe and we realize it's okay not to have all the answers. It's okay, even beautiful, that there is so much we don't know. It gives us room to be curious, to be astonished, to be human.
The night sky remains as it was for our ancestors, profoundly mysterious, compellingly beautiful. We have explanations for the points of light now, suns, not God's campfires or what have you. But the experience of awe is undiminished. If anything, knowing how vast and how ancient those stars are makes the night more awe-inspiring. The knowledge and the mystery together weave the full tapestry of wonder. Science and poetry meet when we confront the sublime.
In that spirit, we end not with a conclusion, but with an embrace of the open questions. The universe's narrative is still being written, and we are part of the writing. Our knowledge will continue to grow, but never exhaust the mystery, and thank goodness for that. The cosmic silence is not emptiness. It is a canvas for our curiosity and imagination. The stillness is not lifeless. It is pregnant with all that we have yet to discover. And the birth of a question is perhaps the greatest gift that the darkness gives to the light of mind. We remain, as ever, small creatures with big minds, suspended between the infinitesimal and the infinite. We seek, we find, we question again. The cosmos doesn't hand us a manifesto of meaning or a clear roadmap. It simply is. But through our not knowing and our relentless pursuit to know, we craft a meaning. In the quiet dialogue between our minds and the stars, we find meaning in the very act of seeking. And so, let us cherish the mysteries. Let us cradle our ignorance softly, not as something shameful, but as the wellspring of all fascination. When we feel that itch of the unknown, when a child asks, why, how, what's beyond, or when we ourselves stare at some deep paradox of physics and feel perplexed, let's smile. That is life. That is the universe, nudging us onward. Each "I don't know" is an invitation. As long as we accept these invitations, we are truly alive, truly participating in the cosmic story. In the vast darkness, a question was born, and from that question flowed all our science, art, and dreams. We do not know all the answers, and likely never will, but we continue, eyes open in the dark, hearts receptive to wonder. For it is in not knowing that we remain curious, and it is in being curious that we remain alive in the fullest sense. The universe, speaking through silence, asks us questions in the language of awe and mystery. Our lives are our answer, an answer expressed in exploration, in love for truth, in reverence for the unknown. In this way, to not know is not just to be alive, it is to be authentically, exuberantly alive, a participant in the grand adventure as old as time and as wide as space. So let the mysteries be, and let us embrace them. Under the silent stars, feel your heart beat with both wonder and peace. The cosmos is vast and strange, and we are an inseparable part of it. In our very inability to grasp it whole, we find our place within it, searching, discovering, and marveling. This is our endless story, the slow, poetic, immersive journey through a universe of questions. And as long as questions remain, life remains vibrant. To question is to live, and to live is to bask in the unknown, even as we reach for understanding. Indeed, to not know is to be alive.